My screen is visible to all.
Yes,
Is
sir.
it?
Yes, sir.
Okay, thank you. So, once again, good afternoon to everyone. So, let me remind you, yesterday we discussed about to higher order neural network, specifically functional link artificial neural network or FLAN. Thereafter, we discussed about one popular metaheuristic or evolutionary optimization algorithm called chemical reaction optimization or CRO. Okay, so yesterday I explained the architecture or structure of a plan, the computation of a plan, and the learning used for plan, I mean back propagation as well as chemical reaction optimization. I skipped it, back propagation algorithm since it is very basic, and I hope the previous research persons they might have discussed about back propagation algorithm for neural network, right? So today let us discuss about one more popular higher order neural network, that is pi sigma neural network, PSNN. P stands for pi, mathematics symbol pi. S stands for sigma, mathematics symbol sigma, and neural network. So this neural network is another higher order neural network which uses pi of sigma, right? So please have a look on the diagram. From the left right, when we are moving on the leftmost side, you can see that this is the input layer. So let the inputs are x1, x2 up to xn. N number of inputs are there, or the input vector size is n, right? And the oval size, actually it should not oval size, it should be a circle. It represents a single neuron. But for simplicity, for the sake of simplicity, I wrote the computation inside the neuron. That's why it become oval. Okay, so each oval is nothing but one neuron, right? So after the input layer, one hidden layer is there, and it contains let m number of neurons. So please look at the first neuron where I wrote z1 equal to summation of w1j into xi plus b, then comma a1 equal to sigma one activation function sigma of z1. So like a conventional traditional neural network, we compute weighted sum at each hidden neuron. Let the weighted sum is z1, and when applying activation on z1, let the output of this neuron be a1. Similarly, the output of the second neuron will be is a2, and like this, the output of mth neuron is am. Right? This is the hidden layer computation. And as a similar to artificial neural network, general conventional artificial neural network, each link from input to neuron, I mean the arrow mark shown on the diagram is associated with some weight values, right? Then coming to the output, on the right hand side there is one it is which pink color, reddish color oval that represents the output neuron. So for the sake of simplicity, I used a single neuron at the output, right? So this network has three layers: input layer, output layer, and one hidden layer, right? I explained the computation at the hidden layer. Now coming to the output layer, where I wrote z, capital Z equal to summation symbol wi into ai plus b stands for bias, and when applied activation function on it, let the output is a, small a, right? So there is a small mistake actually. At the output neuron, I should use pi symbol, right? But by mistake, I used again sigma symbol. It should be pi, right? And the network output will be computed with the original output, or that is called your target. The target is, let the target is y, and the difference will be calculated. The difference is called error, and the error will be back propagated through network, right? And According to the error function, the weight and bias will be updated. But what is the speciality pi sigma neural network? It uses pi of sigma at the output neuron. It calculates pi means multiplication of summation, and there is only one label trainable weight. Where is that? The weight set between input layer and hidden layer. They can be updated, or they are called trainable weights. Whereas the weight between hidden layer and output layer is fixed, is a constant weight, unit weight. Let it be 1. Right? So we need not to update, we need not to adjust the weight between hidden layer and output layer. Rather, only we have to update the weight between input layer and hidden layer. Right? So like emotional link artificial neural network, this is also another flat network because only one layer trainable weights are there. Right? On the right hand side of the slide, I have written computation in pi sigma neural network. So calculate the output of the hidden neuron zj equal to summation of wij into xi. Apply activation function, then it will be aj, and at the output layer calculate pi of output from all hidden layers. Okay, and let the output is called y cap equal to one activation function. Within bracket I wrote pi of aj. So aj means what? These are the aj's are the outputs of the hidden layer neurons. Now we calculate the multiplication of these sigma values aj and then calculate the error. Okay, so this is pi sigma neural network, which is another popular higher order neural network. And you can alter the pi and sigma. For example, in the hidden layer neurons, you can compute pi, and at the output neuron you can compute sigma. So in that case, we can say that the network is sigma of pi values. So pi is not that 3.142, pi stands for multiplication symbol. Okay. So this is simple. The implementation is very simple, and for updating the weights between input and hidden layer, either you can use the traditional back propagation algorithm, gradient descent back propagation algorithm, or you can replace back propagation algorithm or a derivative based algorithm with derivative free algorithm, I mean evolutionary optimization algorithm. Right? So I applied many evolutionary optimization algorithm to train pi sigma neural network, like genetic algorithm, CRO, and other few other firework algorithm, few other optimization algorithms. Right? And computation is very less compared to traditional artificial neural network. It is very similar to functional link artificial neural network. Only the difference is, in case of a plan, we generate the higher order of inputs through expansion block, whereas in case of a pi sigma neural network, we generate higher order of input values through the pi and sigma operations. Okay, so this is your pi sigma neural network. Now let me skip this, because yesterday we have already discussed reaction optimization algorithm, and we already discussed what are the advantages of CRO. I want to remind you, the CRO does not necessitate any algorithm specific parameters. We need not to fine tune any control parameters. Only we have to only we have to determine the value of a reactant number, I mean the population size. So defining the population size is enough. Okay, and we discussed about how we can hybridize CRO with a plan. Few implementations also I demonstrated yesterday. So yeah, so this is another simple explanation about CRO plus a plan process. Please look at the left hand side of the slide. So there is a matrix or a table where this table is called one population or reactant. Reactant means a set of molecules, right? So if you compare with your genetic algorithm, this is simple nothing but a population where each row, I mean each row contains W11, W12 up to W1n. Similarly, the second row W21, W22, then W2n. Like this, each row is called one individual or one molecule. In terms of a chemical reaction optimization, each row can be assumed as one possible molecule, and one molecule can be assumed as one possible solution in the search space, right? So we are trying to find out the optimal weight and bias for the plan or for the pi sigma, which can give maximum accuracy, right? So our job is to update weight and bias so that the error function will be minimized, right? So to do that, let us consider each molecule as a potential candidate in the search space, right? So let the search space contains m number of molecules, m number, small m for stands for mango, m number of molecules, and all these m number of molecules constitute one reactant or one population, right? Where the size of each molecule, I mean length of each molecule, is n, right? So let us start from this initial reactant or initial population and just consider one row or one molecule, train the functional link artificial neural network. Then as for basic CRO, you can find out or you can go with the unimolecular or bimolecular, inter wall collision or intramolecular collision. For example, if you select one row, I mean one molecule, you can apply decomposition reaction or you can apply redox reaction. Whereas if your selection gives two molecules, I told you yesterday that the molecules will be selected on a probabilistic value. Okay, so if two molecules are selected, then you can apply either synthesis reaction or a displacement reaction or a decomposition reaction. Redox 2 reaction. For single molecule, you can apply your decomposition reaction or redox 1 reaction. Okay, so apply chemical reaction optimization on these individuals and in the network, compare both outputs. Here enthalpy is nothing but your fitness function. Enthalpy is nothing but your fitness function. Once again, I repeat, let us consider a single row from this population, apply decomposition reaction, and train the plan with the original molecule along with the molecule which is generated after decomposition of the original molecule. Train plan with both of the molecule, both the old one, original, as well as the new, or that is called your product. Then for both of the reactant, both of the original as well as new products, calculate the enthalpy, I mean your fitness function. Your fitness function can be your mean squared error, or it can be your mean absolute percentage of error, whatever you consider. Compare both of them, okay, and select the best one, or the best one will be carry forwarded. So like this, the process will continue, and finally, when the population, I mean when the reactant will become inert, when it will become converged, that means after that point you cannot find new products, right? So that is called your inertness of your solution, or in terms of a chemical language, you can say that the rate of forward reaction is equal to rate of backward reaction. So this is called your termination condition. Then stop there and find out, identify the best molecule which gives the lowest or the minimum error. That is your nothing but your most suitable solution. Okay, so before going to the new optimization algorithm IFA, I want to map these things to you. Okay, now few limitations are there with the CRO, with the basic CRO. When I'm talking about CRO, I'm talking about the basic, the standard CRO. Few limitations are associated with the CRO. I identified two limitations, drawbacks. The first thing is the quality of initial solution. The quality of initial solution or starting solution. For example, in this diagram, the left-hand side table can be assumed as one initial solution or starting point. Right? So if our search process will start from good point or good initial point, then definitely we can reach the best point easily and with the faster compared to worst solution, right? So the starting point is important, right? Usually, in case of all evolutionary optimization algorithms, what we are doing, we start with random initialization. We start with a random initialization of the population. I mean, generate the initial population with some random values, right? That random value may or may not be a suitable starting point, right? So if it will be not a suitable starting point, then it definitely it will influence the final value or final output, right? So this is one limitation. Another limitation I find out local search. You might have heard about from the earlier presenters or resource persons. You might have heard about every optimization algorithm has two operations: exploration as well as exploitation. Right? Exploration stands for your diversification. Exploitation stands for your intensification. I mean, exploitation is more related to your local search, how deep you can go, right? So, CRO has weaker local search ability, right? So, in order to avoid these two drawbacks, I can't say that the drawbacks, in order to improve the performance of a CRO, these two things, two factors must be handled. So I implemented another improved version of CRO where I addressed these two limitations. Okay, how I addressed these two limitations? First of all, using a good starting point, or that is called your initial population generation method. Right. So what I did here, in place of taking the random initialization, population initialization, I used 4 methods to initialize the population, and I found out the best n number of populations from all those 4 population. I mean, I considered the intersection. What is that called in case of your set theory? I forgot. Okay, I will show you the diagram. So, yeah, please look at this diagram. Look at the upper part of diagram where I wrote initial population. So before initial population, what I did, I generated the populations using 4 methods. The very common method is random population and opposition population. There is a concept in data mining or machine learning that is called your opposition based learning, OBL. So from that concept, I used opposition population. I mean, if there is a value called X, it's opposite value. Right? So if one population is a random population, you can consider simultaneously, you can consider the opposition population or opposite population. And I considered generalized opposition population as well as quasi-opposition population. So few very simple mathematical formulas are there to generate opposition population as well as generalized opposition population, GOP, as well as quasi-opposition population. So initially I started with 4 population parallelly, and I evaluated all the 4 populations, and I identified the best population from all those 4 populations, and I stored it in another population that is called your initial population. Right? Like and other operations of CRO we have discussed yesterday, whether to go for intermolecular collision or intramolecular collision, then how to apply different chemical reactions. Here chemical reactions are nothing but the search operations. The search operations which are applied on a search agent, I mean individual, right? So allow CRO to select the best molecule, and on these best molecules apply NMSA operators. NMSA stands for Nelder-Mead simplex algorithm. Nelder-Mead simplex algorithm is a very simple mathematical algorithm which is used for a local search. It is one efficient local search mechanism, right? So I integrated this Nelder-Mead simplex algorithm with chemical reaction optimization, right? So two things I incorporated to the standard or a basic CRO. One is your initial population generation method, another is integration of your Nelder-Mead simplex algorithm, right? So with these two incorporation, two methods, I achieved better accuracy or better solution compared to the standard CRO, right? And I termed this method as ICRO, improved chemical reaction optimization. I used this improved chemical reaction optimization for global function optimization, as well as another higher order neural network that is called your dendritic neuron model, DNM, right? And recently I published one article on this in IEEE Access. So I request please go through the articles. And if you have any queries, please you can communicate it to me. Okay, so this is your initial population generation algorithm. You see, 4 for loops are there, right? So each for loop, first for loop at the line number 5 is nothing called your opposition population. Then another for loop is there at line number 8. It is quasi opposition population. The third for loop is there at line number 11. That is your generalized opposition population. And finally, consider all the 4 operations. P means your random population. OP means opposition population. QOP as well as GOP, right? And select the best molecules from all these, right? And this will be a good starting point. And these are the operations of Nelder-Mead simplex method. So it consists of 5 steps. So I'm not going in details. Rather, the steps are very simple. And in literature, you can find implementation of Nelder-Mead algorithm also. I hope it is there. Otherwise, it is very simple to implement, very straightforward. Only few steps are there, right? And I proposed this new algorithm optimization method improved to CRO. Then yes, so as I told, I used one dendritic neural model. On the right hand side you can see one neural network like a functional artificial neural network. In place of this network you can use PSNA, you can use FLAN, you can use any artificial neural network. On the left hand side it is your ICRO. Okay, and I applied this method on financial time series forecasting. So these are the major steps. I collected the real life data sets from Yahoo Finance, and I generated the financial time series. Then yesterday I told you how to generate input patterns from the original time series using moving window or sliding window. Then I generated input patterns. I normalized them. You know what is the normalization in data mining technique? Then these normalized data along with the molecules from ICRO at the lower part of the slide, this represents one molecule. So this molecule along with the normalized data, are given the dendritic neural model DNN, so it is produced one output, right? So in place of a DNN, as I told you, you can use other neural network also. Okay, so this is all about your optimization as well as its one of its improved version. Okay, so just a minute. I want to show you. Yeah, I hope my screen is visible. My MATLAB editor is visible to everyone. So here I used functionally artificial neural network and a genetic algorithm, not a CRO. This is not a CRO. Yesterday I have shown you CRO. Rather here I used genetic algorithm, and yesterday I have shown you Dow Jones Industrial Average data set. Another application is there. I used cryptocurrency dataset, that is a Bitcoin dataset. I used monthly Bitcoin value. Bitcoin is a popular cryptocurrency, right? And in the similar way, yesterday I have shown you. I used neural network as well as evolutionary optimization algorithm. Then I implemented it. Finally, denormalization of the value and plotting the graph. So let me execute this program. Let the number of iteration I will use small number of iteration. Let 50 number of generations or iterations. And I executed it. At any time, you can raise a question. If you ask me a question, please put a break on me at any time. So the graph is shown on the monitor. So the blue line is the predicted value by the model, and the red one is the true value or the target. So you can see that the blue value is exactly following the pattern or the way in which the true values or the red line is moving, right? The value is slightly different, but it is exactly following the pattern. Okay, so you can see the mean absolute error is 1.2430 into 10 to the power 3, and before that RAMSE root mean squared error is 2 point something, and MAP is 0.19. So for better accuracy, better or lower MAP values, we have to fine tune the algorithm specific parameters, right? And if you want to see how the algorithm is working, I used the number of generations. So let's see in each generation how the error value is decreasing. So I can write plot my error value is stored in an array that is called E. So see the error value is decreasing like this, but still it is not converged. So we need to find the algorithm specific parameters. I mean, we need to increase the number of generation or crossover probability, mutation probability like this. The graph is not smooth, right? And if you want to see yeah, so these are the error values, the actual value, true value or target value, and the predicted value. Yes, for example, for the first pattern, the error value generated by the model is 0.0015, and the true value is 0.02, sorry, the estimated value is 0.0246, whereas the true value or the target is 0.0230. Okay, so sometimes the error value is negative. So anyhow, these are the results. Okay. So similarly, I applied this model for another application. This is for cryptocurrency. I applied for another application. Let me show you. Just a minute. So okay. So before that, let me show you the data set. This is another data set. I hope it is visible to all. So if it is not visible, please let me know. So this data set is from compressive strength of concrete, right? So all of you know what is concrete. Concrete has a few ingredients, and if we change the proportion of the ingredient, then its strength will vary. Okay, so this is a real data set, and the first feature or the first attribute is your cement. Second attribute is your blast furnace slag, and its unit. I'm not going through the units. Third one is fly ash. Fourth one is water. Next is superplastizer, coarse aggregate, fine aggregate, and edge, the curing edge. Okay, and the last one is your compressive strength. Okay, so let us have a look on a particular sample, the third sample, right? So if the cement component is 385.0, blast slag is 0, fly ash is 0, water is 186, and superplastizer is 0, coarse aggregate is 966, fine aggregate is 763, and curing edge is 1, then the compressive strength of the concrete will be 6.27 megapascal. Right? So like this, 1030 number of samples are there. 1030 number of samples are there along with the compressive strength. Okay, so the compressive strength depends upon other parameters or attributes: cement, blast, fly ash, water, like this. Okay, so here the compressive strength can be treated as the dependent variable, and other attributes can be used as independent attributes. Okay, or compressive strength is called the response, whereas other are called the predictors. Now 1030 number of samples are here. Now the question is, for all the predictor values, the respective compressive strength values are given. Now the question is, if we will consider another new sample with different proportion of attribute values, then what will be the compressive strength? Okay, I think some technical problems are there. Okay, so this is another example for your supervised learning, right? So let me show you. So I'm using the data set called concrete, and let me execute this. So it will take a few seconds. Yes. Now, is it visible, my screen? See, the blue lines are the estimated values, whereas red lines are the actual compressive strengths. Okay. So in this case, the error is a little bit more, not a satisfactory, whereas the pattern, the model estimation follows the same pattern with the original one. Okay, so let me show you a clear version of this. Let us display up to 100. Okay, so now you can see that how the model following the pattern of original compressive strength series. Okay, so any question? You can see the same way. You can see the MAC, RMAC as well as MAP. Here the MAP which is a little bit higher, 0.38, I mean around 38%. So it is not acceptable. So if you will change, if you will fine tune the control parameters, you might get more accuracy. And I also applied uh, this method to another application. My intention is the same model can be applied to different similar applications, right? I applied it to traffic volume and 1 minute. I applied to software cost estimation, and I applied to insurance dataset. I applied to crude oil dataset. Then I applied to IoT time series data also. So let me show you just 1 minute. This dataset is IoT time series data. So overall, I designed a few predictive systems, hybrid predictive systems. Artificial, the base architecture or the base model, the underlying model is artificial neural network, higher order neural network, and learning algorithm. Yeah, this is the output. I think it is overlapped. Let me once again execute this. And the learning algorithm is evolutionary optimization algorithm. Please wait for a few more seconds. Yes, you can see the original IoT time series or response value as well as the predicted value. Is it okay? So this is the overall description of your higher order neural network as well as evolutionary optimization algorithm. And if you are currently working on evolutionary optimization algorithm, better try to get some improvement or modification on existing algorithms, apply to new areas, and before applying to new areas, you must have to evaluate your improved algorithm or modified algorithm with some benchmark optimization function, right? Any questions? Okay, if no questions, let me go ahead. These things we have discussed yesterday. So now let us go with another new optimization algorithm that is called your artificial electric field algorithm or AEFA, AIFA. And originally this algorithm is proposed by one Indian researcher, and it is based on earlier I discussed about the CRO. CRO is inspired from the natural phenomena of natural chemical reaction. So that is one chemistry inspired or chemistry based optimization algorithm. Whereas this artificial electric field algorithm is inspired by the uh, or physics. So this is a physics inspired optimization algorithm. Right. So let us discuss the concept of IFA, how it is motivated uh, from physics or physical science, on what basis it exists. Then slowly, in the next slide, I will try to relate this IFA or the concept of IFA with other evolutionary optimization algorithm. Then we will frame out IFA algorithm. Then I will demonstrate applications of IFA algorithm. So basically, I will explain you, I will demonstrate to you how IFA can be used for global optimization. Right. So I hope I am audible to everyone as well as my screen is visible to everyone.
Yes, sir.
Thank you, sir. So it is motivated from the phenomena of Coulomb's law of electrostatic force between two charged particles. We know that if two charged particles are there in an electric field, then they can attract or repel each other, and the force of attraction or force of repulsion is based on Coulomb's law of electrostatic force. It is based on the theoretic idea of charged particles. You please remember few terminology related to IFA: the charged particle, electric field, and force of attraction or repulsion among charged particles. Okay, underline the word charged particle, electric field, and force of attraction. Just like in CRO, I told you the molecule and the reactant, different chemical reactions. Okay, so the molecule is nothing but the individual or the source agent, and a reactant is nothing but set of source agent, I mean population, and set of chemical reactions are nothing. They are very similar to your source operations which can be applied on a source agent. Similarly here, the charge particle can be treated as the basic or the individual, and electric field, it can be treated as the source field, source space, and force of attraction or repulsion can be assumed as the operations on charge particle. So I wrote the same thing: charge particle as an agent in the source space. Okay, you remember in a source space, the charge particle is treated as source agent. Just like in a genetic algorithm, the source agent or the basic agent is nothing but the chromosome. Okay, in particle swarm optimization, it is called one particle, right? Or in case of teaching learning based algorithm, it is called one learner, student. Okay, similarly, in case of IFA, the charge particle is treated as the basic source agent. The strength of such agent can be measured in terms of charges it possesses. As I told you, a molecule, the strength of a molecule is is measured in terms of sum of potential energy as well as kinetic energy, that is called enthalpy. Or in terms of optimization algorithm, you can say that it is fitness. So the fitness, if a charge particle is the basic agent, then its fitness is nothing but the strength of this agent. So what is the meaning of strength of charge particle? The total charge possessed by it. Okay. Many particles are there in an electric field. So if n particles are there, assume that n number of particles are there, and they are allowed to interact with each other, to communicate with each other, like sensors. So they can interact themselves through charges they own. Right? Means if two charge particles are there, Q1 and Q2, let Q1 has more energy charges and Q2 has less charges, then Q1 can attract Q2 towards itself. Okay, so through this type of attraction, due to a different level of charges possessed by them, is called force of attraction. or they can be used to update the charge particles. The position of these charges are measured as a potential solution problem undertaken, and particles with lower charges are attracted towards a particle with highest charges. And the particle in the electric field, the particular particle or the charged particle in the electric field which has highest charge is called the best particle, or it can be treated as the best solution, the best potential solution for problem undertaken. So I hope everyone got it. You just relate to your particle swarm optimization, PSO. So here there was a particle, here is also a particle, but this particle is considered as a charged particle. The particle has possessed or associated with some charge, right? And the force of attraction or repulsion can be used to update, or can be used as the search operation. Okay, so let us go ahead. Yes, so little bit mathematical things are there. So I extracted these mathematics from the original paper. The charge associated with ith particle. Suppose there is one electric field and n number of charges are there. At a particular time t, let the charge associated with a particle, let the particle is ith particle, that is called QIT, is equal to small QIT divided by sum of this charge QIT for I equal to 110, right? So there is a new term, small QIT. Actually small QIT is the charge. Okay, so a small QIT is a suitable charge function. How it is calculated? It is calculated, the function is given e to the power, then fitness of a t minus fitness of worst particle. Worst particle means the particle having lowest charge, divided by the best particle, I mean the particle having highest charge, minus fitness of a worst particle. So this way we can calculate small QIT as well as capital QIT. Please remember the difference. Small QIT is a charge function and capital QIT is nothing but the charge with the ith particle. That ith particle is treated as the basis source agent, right? Then the force experienced at ith particle holding charge QT due to another particle, jth particle, holding charge QJT is equal to a formula is there, right? Here D is the dimension. So Fij dt means the force experienced at ith particle due to jth particle at time t, right? So look at the formula. There is a new term KT. Okay, and the formula is looking a bit complicated, but it is not that much complicated. So what is the meaning of KT? What is the significance of KT? KT equal to A0 into e to the power minus alpha into iteration divided by maximum iteration. So here this KT is called the Coulomb's constant. KT is called the Coulomb's constant. Sorry. Anything you want to add on this slide? So you just remember three things. The charge associated with the ith particle, and two things, charge associated with the ith particle, that is called capital QIT, and the force experienced by this charge particle. that is capital Fij dt, right? And while calculating, one constant is there called Coulomb's constant. I will show you how to calculate this Coulomb's constant. The formula is there, but while demonstrating you, I will show you how the value of this Coulomb constant can influence the performance of IPA. The performance of IPA is highly influenced, affected by the value of Coulomb's constant. Okay, so let us go to the next slide. Then the resultant electrostatic force acting on ith particle. See, the previous formula Fij t, it is the force experienced at ith particle due to jth particle, another particle, jth particle. Similarly, so many other particles are there, j, k, l, m, right? So the resultant force experienced at ith particle due to all other particles, that is called your resultant electrostatic force of attraction. So it is nothing but summation of force experienced at ith particle due to jth particle into a random value. Okay, and based on this resultant electrostatic force Fid, we can calculate electric field EID. So it is nothing but the resultant electrostatic force divided by the charge associated with ith particle. Okay, so based on this electric field EID, we can calculate the acceleration. See, if two charge particles are there, one is possessing higher charges and other is lower charge, the higher charge particle can attract other. So how the, in what speed or how fast the charge moving towards other. So you can calculate the acceleration. Okay, so to calculate the acceleration, one formula is there, AID equal to QIT into EID of t divided by MIT. MIT is the unit mass, right? So the formula may not have exact significance, but the inventor of the algorithm tried to mimic the natural physical phenomena in terms of one optimization algorithm, right? So we can calculate acceleration, we can calculate velocity as well as a position, and the velocity and position of ith particle in the next iteration will be updated using this formula. The velocity is vi. The velocity in next iteration or next time t plus 1 equal to a random value into earlier previous velocity in the previous time or at the time t plus acceleration. Similarly, the position xid at t plus 1 is can be updated by the previous position plus velocity at t plus 1. Right, so you assume that one electric field is there, in a number of charge particles are there. Charge particle can interact with each other through force of attraction, and due to this force of attraction, they have a certain velocity as well as position. And at the tth time, let the velocity is vi of t, and the position xi of t. So in the next iteration or in the next time value t plus 1, how they were updated. They are updated using these two formula showing at the bottom of the slide. Okay. So please try to relate the concept of electrostatic force of attraction with your standard optimization algorithm. Don't focus on the complexity of the formula. Formula is very straightforward. If you write a small line in MATLAB, it will calculate it. So rather remembering the formula, please try to remember the concept. Okay, so I would like to remind you once again, the charge particle, the associated with ith particle, then the force experienced at ith particle due to jth particle, then the resultant electrostatic force due to all other particle, then calculate electric field, compute acceleration, then update velocity and position based on this acceleration. That's all the concept of IPA. So I hope everyone understood. Otherwise, please, if you have any question, you can put a break on me. Okay. The basic agent is your charge particle, and the search operator is your force of attraction. Then updation. Updation means update the velocity and position of ith charge particle. Okay, so based on this basic concept, let's frame one flowchart or algorithm for alpha. So in the next slide, it is the alpha process. So the first step is randomly initialize the positions of the particles. The positions are represented by x1 t, x2 t up to xt. So the I value varies from 1 to n. It is stands for the number of particles, and t stands for at a time t. Let at a time t, the position of the particles are these. Then set iteration value equal to 0. Evaluate the fitness of each particle. So fitness means, as I told you, the amount of a charge possessed by a particle. But when you are assuming, you are looking the concept in terms of optimization algorithm, evolution optimization algorithm, you can consider that this is nothing but the fitness means the amount of particle. Now, based on these fitness values, identify the best particle, the worst particle, and compute the Coulomb's constant K, acceleration A, and force F. And since at a time t, you can say that K of t, best t, worst t, AI of t, and F of t. After this calculation, update the velocity and position of each particle using these two equations. Update the velocity v and update the position x. Now check the stopping criteria. So the stopping, as I told you, the stopping criteria can be the maximum number of iteration, or it can be a threshold for your error function value. So if you are not attaining the stopping criteria, then you iterate it one more time. Otherwise, if it is matching the stopping criteria, then stop. Identify the best solution. I mean the particle having highest charge. Then return that best solution as the output of IPA. Okay, so with this, let's have a small or short break for 5 minutes. Now it is 4:07. Again, we will assemble at 4:12. Good afternoon once again. Let us resume. So this is the IFA process, IFA flowchart. Okay. Now after this, I hope I am audible to everyone. Then next, I am going to demonstrate to you one simple implementation of your IFA. Okay. And this implementation is not done by me exactly. I slightly modified it. I collected it from online sources, right? So this is the main file of IPA. Then let us consider with the 50 number of. Let us go ahead with the 50 number of charge particle n equal to 50. Am I audible? Can I have a response, please? Hello. Am I audible? Can I have a response, please, from the audience? Anyone of the audience?
Yes, sir, you are audible.
Okay. Thank you, ma'am. So let us 50 number of charged particles n equal to 50. As I told you, a charge particle is the basic source agent of IPA. Then let us consider maximum number of iteration. Let us go with a small number of iterations. Okay, and here f check 1 r1 is some parameters related to your selection of functions, so leave it. And tag value equal to 1 means it is a minimization problem, and 0 means it is a maximization problem, right? I hope that the previous presenters, resource persons, they might have discussed about global optimization functions. Have you heard about Ackley functions, Rosenbrock function, Sewell function? So these are the standard or benchmark function used for optimization, right? And out of those, a few are minimization and few are maximization of problem, right? So the optimization means it can be minimization or it can be maximization. So I'm not discussing about those functions. Those functions are already available in many sources as well as in MATLAB also, or in Python also. If you want to see those functions, if you can implement it easily, you need not to code it. Codes are available. You can see a 3D diagram of these functions. Okay, so let us go with the minimization problems, right? Means see, for what value of x, the function will give the minimum value, right? So this is a minimization problem. And in opposite manner, you can say that what value of x, the function will give a maximum value. That is called your maximization problem, right? Now, generate some random populations and call IFA function. Here is the function call. There is another file. Its name is IFA, AEFA. That IFA contains the basic code of IFA algorithm, right? And this is a master code or a main function, right? So we have to pass the function name, whether it is a Ackley function or Rosenbrock or whatever may be, the number of charge particle n, maximum number of iterations, f check, tag value, and r value. So with these parameters, the function IFA will be called, and function will return after execution. It will return the f best. F best means the best particle, right? This is our objective, to find the best particle. Best particle means the particle having highest charge, or the particle having best fitness value, right? Similarly, L best means your worst solution. Okay, and what are the best values as well as the mean values, right? And finally display the best value. Okay, this is your main function. Now coming to your IFA process. So this is the function IFA. Okay, as I told you, this is the function. I highlighted that function with the highlighted arguments. The argument will be function name, an, maximum iteration, check, tag, and rbar, and it will return these. So here V stands for the velocity. I told you what is the velocity. A is called acceleration. Then we discussed how to compute the acceleration. Q stands for the charge associated with a particle. It will be calculated by sum of small qi. Then D is the dimension of your test function. How many dimensions you want to consider. N is the number of a charge particle. X is the position. R is the Euclidean distance. Distance between charge particle in the search space. The distance between two particles, generally we will consider the Euclidean distance between two charge particles. And for the variable, we may consider the lower bound as well as the upper bound. Okay, and then based on this dimension, I mean lower and upper bound, you fix this one. Then let us create one random position. Okay, and some velocities, initial velocities with 0 values. Then the computation starts from here for iteration number 1 to maximum number of iteration. So first, like all other evolutionary algorithm, first what you have to do, initialization. So this part is called your initialization. Okay, and next is your fitness evaluation. So this loop is for fitness evaluation, and next is application of search operations, right? So yes, before that, how to fitness, these are the codes to evaluate the fitness. Okay, so now from here onwards, calculate the charge, the force, electric field, acceleration, as well as the velocity and position. Okay, so you can see this is the formula to calculate the charge. As I told you, the charge associated with ith particle at a time t or iteration I, that is your qi. So this is the formula. Let me show you the formula, then I will show you the corresponding code to calculate the charge. This is the formula written in the second line. So I think it is visible to everyone. The second line is used to calculate, sorry, the first line is used to calculate the charge associated with the ith particle, and qi is calculated as shown in the second line, right? So please remember this function and see how it is calculated in MATLAB. So this is the equivalent code in MATLAB to calculate q. Okay, see, qi of t equal to small qi of t divided by sum of qi of t. So where it is shown? It is shown here. I highlighted that line, right? But small q is calculated with this formula. I highlighted just. Okay, now just skip this. These are the calculation of distance, and this is the calculation of Coulomb's constant. So experimentally, inventor of this algorithm, they found that the alpha value the standard alpha value for alpha is 30 and k0 equal to 500. Then based on this k0, calculate k, Coulomb's constant. So I will show you how the Coulomb's constant value influence the performance of alpha. So these two, I mean alpha and k0 are the tuning parameter of alpha. Whereas in case of a CRO, it has no tuning parameters. We can say that it is a parameterless. But alpha has two parameters, alpha and k0. If we change the values of alpha and k0, the performance of alpha will also change. Okay. Then next line is calculation of acceleration. Then next three lines are for velocity as well as position of destination. Okay. Then next few lines are for displaying purpose, graphical use. Let us graph. Okay, so these benchmark functions, so many benchmark functions are here, starting from here. This is the first benchmark function. This is second benchmark function, third benchmark function, like this. And yeah, this is the 10th benchmark function. I think it is Achille function. Okay, so similarly, so many benchmark functions are there. Then you have to choose the benchmark function for which you want to find the value for which the function value will be minimum, because we are going with a minimization problem. Okay, then another thing is that fixing the bound, upper bound, lower bound of a particle, right? So for example, if the function number will be 10, I mean for Achille function, let us consider the lower bound is minus 32, upper bound is plus 32, and the dimension is 30. Actually, you can find the formula of these benchmark functions. There is one site called CEC, Congress of Evolutionary Computation, like this. So benchmark functions along with their dimensions are specified there. And when you are proposing one new optimization algorithm, or when you are claiming improvement or modification on existing algorithms, you must have to first test your method on these standard benchmark functions. Okay, so these are the ranges. So let us execute the code, and remember we are going with alpha value equal to 30 and Coulomb's constant value equal to 500, number of a particle 50 here, and maximum iteration 10. Okay, so let us execute. I hope my screen. See, the blue particles is 50 number of particles, right? So there are 49 number of blue stars and one red star. The red star indicates the particle, and whereas all the stars, whether it is irrespective of the color, all the stars represent one charge particles, and the search space, the whole 2D space, can be considered as one electric field. So with the 10 number of iterations, you can easily see that all these stars are not converging towards the best particle. So let us increase the number of iterations. So let us make it 50. I changed the maximum iteration to 50 here. Okay, so let us execute it. Now you can see how the particles are moving towards each other in each iteration. So still all the particles are not converging towards the global best red mark. So let us increase the maximum number of iteration. Let it is 80. Please look at the behavior of the particles. See, through the iterations, they are converging towards the best, and the global best value is nearer to 0. Okay, so you can see how the particles converge to each other, and you can see the best value is here 1.2129 into 10 to the power 3. Okay, but still it is not acceptable. Let us increase iteration to 100. Now look at the movement of the particles. And in the command window, you can see the F best value, that is 1.0555 into 10 to the power 3. Okay, so it is converging in around 100 number of iterations. So let's change one more function. Let us go to so let us go for actually function. The function number is 10. Now see the now see the best value is 6.8350. Okay, so for the same function, let us see how the function value, the performance of I5 is influenced by the Coulomb's value, Coulomb's constant. Yes, so here we have considered k is equal to 500, and based on that calculated the Coulomb's value k. Okay, so let us make Coulomb's k0 value 100. Then execute it. So my suggestion is, if you are going to use evolutionary optimization algorithm, at least first implement a few existing algorithms, whether it is genetic algorithm or PSO or DE or LBO. First try to implement one basic algorithm, then apply to your problem. Then you can go for further improvement or modification. So now the value is changing, a best value is changing with the value of Coulomb's constant. If we make it k0 equal to 10, let us see how it is behaving. Actually, Coulomb's constant is just working as a jumping variable, a jumping factor. How fast a particle can move. Okay, so see, for this Coulomb's value, for new K0 value, I mean its value when I fixed to 10, see the best value is 20.0349. So it is not acceptable. Okay, and if we increase the value beyond 500, let us see what happens. Let's make it 700 or 800. Then now you may ask me how to fix the value of K0. Actually, there is no standard rule. These are called the tuning parameters. So there is one existing method called Taguchi method. So you can consider uh, uh, finite number of combinations using the method is I think a Taguchi method. So you can find the proper value. Otherwise, you can go with a trial and error method like this. Okay, so when you are increasing value to 700 or 800, small changes are there. So better go with the standard value, that is 500. And if we change the alpha value, let it 30, let it make it 10. Actually, in one of my recent papers, as I told you a few minutes before, ICRO and DNM. In case of a DNM, also 3 tuning parameters were there. Instead of setting it them manually, I used one evolutionary method. I decided the value of those 3 parameters using ICRO. Right? So there is no need of manually fixing these parameters. Now see, for alpha 10, the best value is 1.155. I think it is a acceptable value. Similarly, if we change the range of function, then you can get different values. Okay, so let us go with the one more function. Since it is one new algorithm, so you can apply this algorithm to any problem and can claim that it is a new application, not novel algorithm. Or you can, one more suggestion, for this IPA, you can consider a new population generation method, multi-population method, and you can try with the integrating Nelder-Mead simplex algorithm with the IPA. Okay, so for function number 12, with alpha value 10, K0 500, number of particles 50, and maximum number of iteration 100, the F best value is 2.0533. So now, one more thing, let us increase the number of particles and see whether you are getting proper or not. I increased the number of particles. Earlier it was 50, I made it 500. So, as you know, optimization algorithms you can utilize for your classification, clustering, or prediction systems. But particularly in my case, I have been designing hybrid prediction systems, right? And you can use it for classification. For example, same plan or same PSN, you can train them the higher order neural network. Either you can go with the plan or PSN or both of them, and you can apply to any real life application. Then it will be a new article. You can easily publish it. Okay. So now the if best value is 1.2580 divided by 10 to the power 10. Then what are other tuning parameters? No, only let us go with the maximization problem. Let us make it tag equal to 0. The same problem, let us go with the maximization problem with the same parameter values. But in almost all my applications, I used adaptive learning. Means since I used financial data and I used sliding window method. So once I found the what it is called the first level optimized weight, then I reduced the number of iterations to a small value. This is called your adaptive learning. So almost all applications I made, I used adaptive learning. And please, I request please go through few of my articles, and if possible, if you will find interest, please cite my articles also. And if you are interested to work for collaborative work, then I'm always open. You are always welcome. Okay, so this is all about your IPA. Okay, though I used IPA for neural network optimization, but the work is going on. I have not finalized yet. That's why I'm not showing you the code, the implementation. So in future, if I will get any opportunity from your faculty in charge, faculty coordinator, Dr. Manjuwala ma'am and Dr. Sanjay Panda, then I will try to demonstrate those things also. Okay, so this is IPA. Then I'm coming to now. Once again, I want to remind you the process of IPA. If you understood genetic algorithm or PSO or any of the optimization technique, evolutionary optimization technique, try to relate these steps with those techniques, right? So all algorithms starts with initialization. This is also starts with initialization. You might see that the first step is randomly initialize. Then the second step is evaluation, fitness evaluation. Third step is calculate the parameters as well as identify best worst charged particles. Next is update the particle, update the velocity and the position, check the stopping criteria. That's all. Okay, so any question till now? So if you will summarize, I started with the higher order neural network, specifically plan, and I gave a small demonstration also on Pi Sigma neural network. Okay, so my objective was to show how higher order neural network are working better compared to the standard artificial neural network or a multi-layer neural network or ALP. The advantages of higher order neural network are they consider higher order terms, and through those higher order terms they can find the amplification of the search space, right? And they are flat network. Since only one level of trainable weight and bias are there, the computation is very less. Okay, and the classification or the accuracy performance is very good. And we discussed about evolutionary optimization algorithm. In the first page, I explained you one chemistry-oriented or chemistry-inspired optimization algorithm, that is called your CRO. Then in the second page, I explained you another physics-inspired optimization algorithm, that is called your artificial electric field algorithm. Okay, and on the part of implementation, I demonstrated you the basic plan with the backpropagation algorithm, how it is working. Then the same plan optimized with the CRO, and improvements of CRO also. Then I explained IFA implementation for global function optimization. Right, this is my summary, and these are the references I used. Few of the references I used, and I request everyone, please find me in Google Scholar. My name is, you just type Sarath Nayak, Saratnay. Okay, you can find few of my articles, and if you are finding interest, as I told you, I request you, please go through them, give me feedback in what other way I can improve myself, or in what way I can help you. And if possible, if you find my articles are interesting and related to your job or work, please cite them. Okay, any question? No questions. Okay, so now it's the time to wind up. I was a bit early, so I think the next presentation is at 5 o'clock. So please take 5-10 minutes rest, then attend the next
Okay, sir.
talk.
Thank you, sir.
And you can contact me. You can contact me, Sarath234 at the rate gmail.com, with the this mail ID. And this mobile number will not work in South Korea, though I have South Korean number, so you cannot access. Better you will contact me through WhatsApp.
Thank you, sir.
Okay, so thank to everyone. Yeah, thank for your time, precious time, and especially thanks to Dr. Manjubala Bisimam and Dr. Sanjay Kumar Pandya sir, to give me such opportunity and to share my knowledge. Actually, for a few days I have been staying in India, and here I don't have a proper setup, but and my health is not good also. But still, I um, I did not skip that the chance given by the professor in charge, Dr. Manjubala ma'am and Dr. Sanjay Kumar Panda. And thanks to all participants attended this presentation, without whom the presentation has no meaning. Thanks to all. So with this, I take permission from Dr. Manjubala ma'am and Sanjay Kumar Panda sir,
Thank you, sir.
and
Thank you, sir.
now I am leaving. Yeah, thank you everyone. Let me leave the session. Thanks
Thank
to
you,
all.
sir. Thank you, sir.
सर नमस्कार सर.
नमस्कार नमस्कार.
स्टार्ट करूया.
हाँ.
You can start, sir. You can share your screen.
Okay. Is it visible?
Yes, sir. Yes. Sir. You can start, sir.
Okay. So thank you, madam. So in the last class, we learned about a single variable unconstrained optimization, where the number of variable was only one. Today, we will deal with somewhat more complex problem where the number of unknown variable is more than one. So in that case, today we will discuss multivariable unconstrained optimizations. Am I audible, the participants?
Yes, sir, you are audible.
Okay. And the slides is also moving. Could you see my second slide now?
Yes, sir.
Yes, sir. Yes,
Okay.
sir.
So here, as the name says, it is multivariable optimizations. Here, the number of unknown variable, that is the decision variable, that is x1, x2, up to xn, that should be more than one. So thus, in the earlier case, in single variable, we were searching in only one direction, that is the x directions. But here, we will be searching in multi directions. If there are two variables, we will search in the two directions, like that. So whenever you search in any one directions, whatever it is as good as a single variable optimizations, and whatever the algorithm that we have learned in the last class, all those algorithm will be applicable whenever our searching is in one direction at a time. And all the algorithm that we have discussed in the last class, and we have solved problems for minimization algorithm, but all those algorithms are also equally applicable to maximization problem by making some slight modification in the objective functions. That is, if our objective is to maximize, not minimize, a objective function, let's say gx, this is as good as minimization of minus gx. Right. So once and minus gx can be taken to be a objective function f of x, and then the procedure is same. Just like in the single variable problem, here also all the algorithm can be classified under two broad categories. One is direct search methods, where we need not have to calculate the derivative values of objective functions. Simply you have to calculate only the function value f, and by comparing those functional values, we can take a decision whether in which direction we should move, or any portion that is to be deleted, etc., etc. And we'll move towards, that will help us to move towards the optimal point. The second category of methods are called gradient based method, where we'll be taking the help of first and second derivatives of objective functions. Under direct search method, there are four algorithms: evolutionary optimization, simplex search or S-square search, Hook-Gibbs pattern search method, Powell's conjugate direction method. In today's class, we'll take one of these algorithm, that is Hook-Gibbs pattern search, and we learn how we can use that algorithm to solve a multivariable optimization problem. Under gradient-based method, the algorithms are Cauchy's method, otherwise also called as steepest descent method, Newton's method, Marquard's method, conjugate gradient method, variable metric method, or otherwise also known as DFT method, that is named after three researchers: D for Davinden, F for Fletcher, and P for Powell. Okay, now let us learn about two terminology, that is gradient vector and Hessian matrix, which are used whenever we solve a multivariable optimization problem. Okay. So whenever, let's say, there are number of decision variables is more than one, So that is capital N is the number of decision variable and it is more than 1. So in that case, a solution is not one value. It is rather a set of n different values. So these n different values will be for n number of decision variables, x1, x2 up to xn. And all these 10 values will constitute one solution. Just like this, we can call it as a coordinate, x1, x2 up to xn coordinates are there. And only when we know the coordinate values of these n coordinates, then only you can able to plot that point or a solution. So here we'll be dealing with not one value, rather a set of n values that will constitute one solution. And that solution will represent by a vector called x. So x with an arrow at the top means a set of n unknown values. And here, actually, the vector x is a column vector, but I have written down these numbers in a row 1. That's why I've written a transpose of it. So transpose means this is a column vector. So the solution vector is a column vector. So accordingly, the function f here is not a function of only one unknown variable, rather it is function of n unknown variable, x1 to xn. So this can also be written by f of x vector. So instead of writing down all those unknown variable x1, x2, or xn, simply you can write down x vector with an arrow. And in the book, you might have observed that instead of writing a arrow at the top, the variable x is written in bold form. Bold form means this is a vector, and plain form means it is a variable or it's a number. Okay. So gradient of a vector, gradient of the objective function f is not a scalar quantity, it is a vector. And this is denoted by del f of x. And this is defined as that is given in the last row. So this is nothing but a set of n number of partial derivative. We have n unknown variable. So for each of the variable, we have to take the partial derivative. First, we have to differentiate f partially with respect to the first unknown variable, that is x1. So del f del x1, then del f del x2. So like this up to del f del x1. So a set of n partial derivative constitutes the vector called gradient vector, denoted by del f x. So this comes in, del f represents, it is analogous to your first derivative, right, in the multivariable problem. But this is not a total, each of the element is not total derivative either or partial derivative. Then the second order derivative is called Hessian matrix in the multivariable problem. So del f, we take one more time partial derivative. So denoted as del second derivative in multivariable problem is denoted as del square f of x. So this is a matrix. So we call it Hessian matrix Hx. So this represents the double derivative of objective function f of x. So here you can see this is a n by n matrix. The Hessian matrix is n by n matrix, where n, capital N, is the number of unknown variable. So what we do here, whatever the vector, that's gradient vector, you have got it, that is del f del x1, del f del x2, del f del x1, that we write down in a row vector, right? Actually, gradient vector is a column vector, but we write down its transpose, that is del f del x1, del f del x2, del f. And this gradient vector, that is del f, we partially, since it is for the first row, so we partially take another derivative, but with respect to the first variable x1. So you do del of del x1 for the del f. Then in the second row, when it comes, the same del f, but we take the partial derivative with respect to x2. Third row, the element will be gradient vector, but we differentiate partially with respect to x3. So like that, x3, x4, x1. The last one will be with respect to xn. So thus, in the first row, there will be n element. Each one will be a double derivative. Similarly, second row also will have n elements. So this will be n row because del x, del x1, del x, del x2, del xn. So there will be n row and n column. So this will be n by n matrix. So when you take del f del x1, we differentiate with del of del x1. The first terminology will be del square f del x1 square. Then for the second one, when you take, it will be del of del x1, then del f del x2. First del x1, then del x2. Then the third element will be del x1, del x3. So for in the first row, the first term will be del x1, and the second term will be del x1 if it is first column, del x2 if it is second column, del x3 if it is third column, like that. But in the second row, the first part will be always del x2. So del x2, del x1, del x2, del x2, del x2, del x3, like this. So thus, the Hessian matrix will be simplified to this one. So del square f del x1 square, this is actually del x1, del x1. Then the second term will be del x1, del x2. The third element will be in the first row, it will be del x1, del x3, like this. The last one will be del x1, del xn. In the second row, it will be del x1, del x2, del x1. The second element will be del x2, del x2 or del x2 square. Third one will be del x2, del x3. Like this, the last one will be del x2, del xn. So like this, the last one, nth row and nth column element will be del xn, or in other words, del xn square. So this will be n by n matrix. This is a Hessian matrix. Now let us define analytically if you can able to solve a unconstrained multivariable optimization problem. Just like in the single variable case, we had already solved analytically. That is, we took the first derivative and we equated to 0. Then we solve it. Then we took the higher order derivative till we get a non-zero value. And if the higher order we get, and if the corresponding order of the derivative is a odd, then that is a point of inflection. If it is even, then it can be either minimum or maximum. So if the derivative value is positive, it is a minimum point. The derivative value, the higher order derivative value is negative, then this will be maximum point. So analogous to that, in multivariable one, the analytical solutions, the corresponding criteria for optimal solution is written like this. So here also a solution or a point represented by vector x, that is a set of n values x1, x2, xn. So this is called a stationary point or an optimal point, analogous to optimal point of the objective function f of x if its first derivative, just like in single variable, first derivative is equal to 0, but in multivariable, the first derivative is called gradient vector. So this is del f del x1. So take first derivative, or that is gradient, that is del f del x1 equal to 0. In single variable case, we are taking first derivative equal to 0, but here it is corresponding terminology is gradient of f is equal to 0. Now further to know that whether this optimal point is a minimum point or maximum point or point of inflection, we have to take the higher order derivative. And in case of single variable, we may have to take double derivative or triple or fourth order, fifth order till you get a non-zero value. But in multivariable problem, you need not have to take beyond the second order derivative. The second order derivative is sufficient. So we just take the second order derivative, that is called Hessian matrix, the del square fx. If this value, this matrix is not a value, it is a vector, no, sorry, matrix. If this matrix is positive definite, in case of single variable, we are just calling positive value. If it is positive, that point is called minimum. But here, in the sense of a multivariable case, which is a matrix, so the corresponding terminology will be positive definite. If it is positive definite, if that matrix is positive definite, which matrix? The Hessian matrix, del square f. The corresponding x will be a minimum point. If it is negative definite, it will be a maximum point. Otherwise, it will be a point of inflection, or also called as saddle point. Let us try to understand how we can check whether a solutions let's say this is a two variable objective functions. The variables are x1, x2, and f of x is written like this: x1 square plus x2 minus 11 whole square plus x1 plus x2 square minus 7 whole square. Now this function, we have to check whether this function has a minimum value, means it has a local minimum at the solutions or the point 3, 2. 3, 2 means when x1 value, coordinate value is 3 and x2 coordinate value is 2. This objective function is called Himmelblau function. Let us check. So f of x is this one. So let us take the gradient vector. Now gradient vector, since it is a two variable problem, there will be two partial derivative. One will be del f del x1, another will be del f del x2. So let us take the first derivative, first partial derivative. So it has two terms. So for the first term, when you take derivative with respect to x1, so this will be twice of whatever is there inside the bracket. Then into the derivative of what is there inside the bracket. So x1 square, the derivative will be twice x1. But when you are taking derivative with respect to x1, x2 is treated as a constant. So that's why for x2, the derivative will be 0. And for minus 11, the derivative will be 0. Now for the second term, there is x1 plus x2 square minus 7 whole square. When you take derivative with x1, it will be to the power 2. So that's twice of whatever is there inside the bracket. So twice of x1 plus x2 square minus 7 into the derivative inside the bracket. So for x1 it is 1, for x2 square it is a constant, so 0, for 7 it is 0. Now on simplifying, we will get 2 into 2x1, this will be 4x1, then whatever is there inside the bracket, plus 2 into 1 is 2, and then whatever is there inside this bracket. Hello? Hello? अच्छा मैं ଗୋଟେ କ୍ଲାସ୍ ରେ ଅଛି ପରେ କଥା ହେବା. Sorry. So this is the first partial derivative with respect to x1 that is shown in the blue color. Now similarly, let us find out for this objective function f partial derivative with respect to x2. So let us do it then. So for the first term, again twice of whatever is there inside the bracket. So twice of x1 square plus x2 minus 11. Then whatever is there inside the bracket, we have to take derivative with respect to x2. So when you take derivative x1 square, it will be 0. For x2, it will be 1. For 11, it will be 0. Then plus twice of whatever is there inside the bracket. Twice of into whatever is there in the bracket. Then into for x1, it will be 0. For x2 square, it will be 2x2. For 7, it will be 0. So on simplifying, we will get del f del x2 is equal to like this. That is written here. There is 2 into 1, it will be 2 into whatever is there inside the bracket. Then plus, this is 2x2 into 2, 4x2, then into whatever is there inside the bracket. So two partial derivative, you got it. So those will be the two elements of the gradient vector del f. Now the solutions at 3, 2, let us find out these values del f del x1 and del f del x2. Let us put it. So 3, 2 means x1 is 3, x2 is 2. So in case of del f del x1, let us put it. So x1 square, so 3 square is 9 plus this 2, x2 is 2. So 9 plus 2 is 11, 11 minus 11 is 0. So the first term is 0. And in the second one, x1 is 3 plus x2 square is 2 square is 4. So 4 plus 3, 7, 7 minus 7 is 0. So 0 into 2 is 0. So 0 plus 0, it will be 0. So del f del x1, sorry. So del f del x1 will be 0. Now let us find out del f del x2. So x1 square plus x2 minus 11. So x1 is x1 square is 3 square is 9. 9 plus x2 is 2. So 9 plus 2 is 11 minus 11 is 0. 0 into 2 is 0. Plus Then x1 is 3, x2 square is 4, 4 plus 3 is 7, minus 7 is 0. So 0 into 4x2 is 0. So 0 plus 0 is 0. That means both the element value is 0 now. Right. At 3, 2, del f del x1 is equal to 0. Del f del x2 is equal to 0. That means at 3, 2, the gradient vector del f is equal to 0, 0. So this is a null vector. So thus, since del f is equal to a null vector 0, 0, all the elements are 0. So it satisfies the first conditions. So we can say that the solutions may be a optimal solution. But whether it is maximum or minimum or quantum inflection, for that we have to take the second order derivative. That is the Hessian matrix. Yes, 3, 2 is a stationary point, and it may be maximum, it may be minimum, or a point of inflection. So now let us find out Hessian matrix. So Hessian matrix, since it is a 2 element, this is a number of unknown variable is 2. So Hessian matrix will be a 2 by 2 matrix. So having these 4 elements. So in the first row, if you see, the first part will be del x1, del x1, del x1. This is del x1, del x2. In the second one, it will be second we will find out del x2, del x1, del x2, del x2. Let us find out. So f is this one. Del f del x1 already we have found it out. Now for the del f del x1, let us now this del f del x1. Now let us differentiate it once more with respect to x1. So whatever is there the del f del x1, let us differentiate with respect to x1. So let us do it. So this is a product of 3 terms and 4 is a constant. Let us take it outside. So x1, when you differentiate with respect to 1, it will be 1. So 4 into 1 is 4. And then we write down whatever is there inside the bracket. There is x1 square plus x2 minus 11. Then plus 4 into x1 into, now whatever is there inside the bracket, you have to take the derivative. So x1 square, the derivative will be 2x1. For x2, it will be 0 because we are differentiating with respect to x1. So x2 is to be treated as constant. And for 11, it is 0. So finally, it will be twice x1. Now for the second term, 2 is a constant. So take it outside. And inside the bracket, let us differentiate with respect to x1. So for x1, it will be 1. x2 square 0, 7, 0. So 1 inside the bracket will be 1. So 2 into 1, it will be 2. So I'm simplifying this. 4 into whatever is there in the bracket plus 4x1 into 2x1 will be 8x1 square, then plus 2. This is del square f, del x1 or del x1 square. So this is the first element of this Hessian matrix. This matrix we have found out just now, del square f, del x1 square. So at 3, 2, now let us put the value x1 in this one, whatever that we have got the second order the partial derivative. Here let us put x1 is equal to 3 and x2 is equal to 2. So x1 square will be 3 square, that is 9, plus x2, so plus 2 minus 11 into 4. Then plus 8 into x1, x1 is 3, so 3 square is 9, so 8 into 9, then plus 2. So 8 into 9 is 72, 72 plus 2 is 74, and here 9 plus 2 is 11 minus 11 is 0, so 0 into 4 is 0. So finally we get 74. So the first row here, first row, first column, that element, del square f, del x1 square at 3, 2, we just calculated that this will be 74. Similarly, let us calculate for the other 3 element. The other 3 element, this 3 element. Let us find it out. So del f, then del f del x1. But this del f del x1, let us differentiate with respect to x2 now. So that we'll be getting del square f del x2 del x1. del x2, del x1. So this is your second row, first column. Let us check it. We are now finding out this element. Second row, first column, del square f, del x2, del x1. Let us find out. So with respect to x2, we have to find out. Okay. So 4 into x1 is a constant. So 4x1, you take it outside. Inside the bracket, x1 square will be 0. For x2, it will be 1. For 11, it will be 0. So 0 plus 1 minus 0 will be 1. So 1 into 4x1, we will get 4x1. Then for the second one, 2, take it outside. Inside the bracket, for x1, it will be 0. For x2 square, it will be 2x2. For 7, it will be 0. So we get 2x2. 2x2 into 2, it will be 4x2. So thus, this is 4x1 plus 4x2. 4 taking outside, it will be x1 plus x2. So let us find out the value at 3, 2. So x1 is equal to 3 plus x2, that is 2. So 3 plus 2, it will be 5. 5 into 4, it will be 20. So thus, the second element value will be 20 at 3, 2. Similarly, let us find out the other two values. Now let us take del f del x2. Already we found out in case of that gradient vector. Now del f del x2, now let us differentiate with respect to x1. So that we will get del square f del x1 del x2. So let us take partial derivative with respect to x1. So 2 is constant, take outside. So x1 square, it will be 2x1 plus x2 is constant, so 0. 11 is 0 plus 4x2. We are differentiating with x1. So x2 is constant. So take 4x2 outside. Inside the bracket. For x1 it will be 1. For x2 square it will be 0. For 7 it will be 0. So thus on simplifying, 2 into 2x1 is 4x1. 4x1 into 1, it will be 4x2. So thus it is 4 within bracket x1 plus x2. So therefore at 3, 2, this element also we have the same value, that is 20. 3 plus 2 is 5. 5 into 4 is 20. Now the last element is del square f del x2 square. So this is nothing but del x2 of del f del x2. So del f del x2 we have got already while calculating the gradient vector. So this let us differentiate with respect to x2. So 2 is constant, take outside. So with respect to x2, x1 square will be 0. For x2 it will be 1. For 11 it will be 0. Then plus. Now with respect to x2, so x2 is a variable. So 4 into the derivative of x2 will be 1. 1. So 4 into 1 is 4. Then whatever is there inside the bracket, x1 plus x2 square minus 7. Then we take 4x2 into the derivative what is there inside the bracket. So this is here 4x2 within the bracket. For x1 it will be 0. For x2 square it will be 2x2. For 7 it will be 0. So on simplifying this, you see 0 plus 1 minus 0 is 1. 1 into 2 is 2. Okay. Plus. This is inside the bracket is 2x2. So 2x2 into 4x2, it will be 8x2 square. Then plus 4 into whatever is there inside the bracket, there is x1 plus x2 square minus 7. Now let us put at 3, 2. So x1 is 3 and x2 is 2. So 2 plus 8 into x2 square. x2 is 2, so 2 square is 4. 4 into 8 is 32. Plus 4 into x1 is 3 plus x2 is 2. 2 square is 4. So 4 plus 3 is 7. 7 minus 7 is 0. So 0 into 4 is 0. So the third part is 0. So we are left with only 2 plus 8 into 4. 8 into 4 is 32. 32 plus 2 is 34. So thus the Hessian matrix, we got all the 4 values. So the Hessian matrix will be 74, 20, 20, 34. So in the diagonal element, it is 74 and 34. And this diagonally, this opposite, the mirror image of along this leading diagonal, this is equal, that is 20, 20. So this is a Hessian matrix is a 2 by 2 matrix because our number of unknown variable is 2. So this is a square matrix. Also, it is a symmetric matrix because about this leading diagonal, the diagonally that opposite, the mirror image element will be same. So this is a symmetric Isman. Lower half and upper half is same. So at 3, 2, the gradient vector is 0 null vector, so it is stationary point. And the Hessian matrix at 3, 2 is a symmetric matrix. Now this symmetric matrix, whether it is positive definite or no, the rule says that if all its leading principal minor are strictly positive, then we can say that this Hessian matrix will be positive definite. Now, what is leading principal minor? Yes, anyone? If they know the leading principal minor? What is a minor? Yes? Am I audible
Yes, sir.
or disconnected? Okay.
Yes, sir.
Anyone, please tell what do you mean by minor? What is a principal minor? What is leading principal minor? Do you know or shall I explain?
Please be kind to explain.
Okay, seriously, let me explain. So let us explain then. Okay, let us first try to understand what is a submatrix. Given a matrix, let's say A, it's, and in this particular example, it's a 3 by 3 matrix. There is A11, A12, A13. So 3 rows, 3 columns. Now, a submatrix of A will be somewhat of size less than this 3 by 3. Means that will be a subset of this matrix A. So to get a submatrix, we have to delete rows and column, right? So for a n by n matrix A, the kth order submatrix will be obtained by deleting some rows. How many rows you have to delete? Because your A is n row, the matrix A has n row, and to get a kth order submatrix, there is k by k matrix, you have to delete n minus k number of rows. So similarly, we have to also delete n minus k number of columns, so that the matrix A will be reduced to, of size n, will be reduced to a smaller size matrix having size k by k matrix. So that is a submatrix. And the determinant of submatrix is called minor, right? So that is the difference between minor and submatrix. Now here we can delete any rows and any column, but the number of rows and number of column to be deleted should be same. Okay. Now let us see. What is a principal submatrix? We can delete any n minus k rows, but whichever rows we are deleting, the corresponding columns, if you delete it, then that will be a special submatrix called principal submatrix, right? If you delete any rows, any column, it will be a submatrix. But if you delete the corresponding rows and column, if you are deleting second row, then second column should be deleted. If you are deleting third row, then third column should be deleted. That means you can delete any n minus k rows, but the same corresponding n minus k column you have to delete. So that submatrix will be called principal submatrix. And the determinant of principal submatrix will be called principal minor. But if you delete the last n minus k rows and last n minus k column, then that principal submatrix will be called leading principal submatrix. And the corresponding determinant will be called leading principal minor. Let us take an example so that it will be clear. Okay. Now, let's say this A is a 3 by 3 matrix, but we want to find a submatrix of, let's say, leading principal submatrix. We have to find out of first order. So k is equal to 1, but n is equal to 3 by 3 matrix, so n is equal to 3. So how many rows we have to delete? n minus k rows and column. So n minus k will be original matrix size is 3, and you will reduce it, submatrix size is k is 1, so 3 minus 1 is 2. So we have to delete 2 rows, 2 column. And to get leading principal submatrix, you will delete the last 2 rows and also the last 2 column, right? So we have deleted this last 2 rows. There is a second row, second column that is deleted by this red hatchet line, and also the last 2 column, that is second column and third column, you have to delete it. So we are left with only one element, that is A11. So this is 1 row, 1 column, 1 by 1 matrix. So this is a submatrix of order 1. And this is a special submatrix. There is a leading principal submatrix because you have deleted last 2 rows and last 2 columns. So what will be the determinant of A11? A11 itself. Then to get a second order LPS, that is k equal to 2. So n minus k will be 3 minus 2 equal to 1. So you have to delete last 1 row and last 1 column. So let us delete. So last 1 row is the third row and last 1 column is the third column. So after deleting it, we are left with A11, A12, A21, A22. So this is a 2 by 2 matrix. So this is a second order leading principal submatrix. And its determinant will be A11 into A22, there is a diagonal element, minus the other 2 elements, A21 into A12. So that will be leading principal minor. And the third order LPS will be how much? So here k is equal to 3 and n is equal to original size is also 3. So 3 minus 3 is equal to 0. That means we have to delete last 0 row and last 0 column. Means we need not delete any row, we did not delete any column. So thereby the matrix itself is the leading principal submatrix of the same size. So if a matrix is a 3 by 3 matrix, we will have 3 leading principal submatrix. There is first order, second order, and third order. Right. So for all these 3 leading principal submatrix, we have to find out the minor, and if all the 3 are strictly positive, then you can call that the matrix A3 is positive definite. In our particular example, so see here, the first order LPS is A11, so this is shown in the red color. Second order LPS will be, including this red color, whatever is blue is there, red plus blue will be your second order LPS. Now all the element, red, blue and black, that will constitute the third order LPS. That means we start with this top left corner element, then we proceed actually towards the right and towards the bottom. So one step we go right, one step we go bottom. So whatever the 2 by 2 matrix is there containing this A11, this is a second order LPS. Then we go one step right and one step here, one step down. Right. So whatever the element is encapsulated, the 3 by 3 matrix. So this is a black, blue and red. Everything is a 3 by 3 submatrix. So if I say the total for this 3 by 3 matrix, how many LPS is there of the first order K1? That already have found out only 1. But there will be principal submatrix, there will be 3. Because there we can delete any rows but the corresponding column. Is it clear? But any row, any column if you delete, there will be 9 submatrix. Each of the element will be forming a submatrix of 1. Let us try to understand principal submatrix, not LPS, principal submatrix. Okay, here. So if you delete because of the k equal to 1, so we are deleting the, let's say, second row, third row. but we can delete, let's say, second row, third column, we'll get A11. But we can also delete. There is no restriction that last two row, last two column in case of principal submatrix. So if you delete second row and third row, but not second column, let's say I delete first column and third column. So I'll be left with only A12. So there is also a principal submatrix. If you delete second row and third row, but not deleting second column and third column, rather, if you delete first column and second column, you will left with A13. So A11, A12, A13 will be the three principal submatrix. But if you delete any row, any column, let's say, so let's say I am deleting second row, third row, and second column, third column, it is A11. But if I delete second row, third row, no, let's say first row and second row, so we are left with third row. And if you delete, let's say first column and third column, we are left with A32. So if you delete any two rows, any two column, each of the element will be getting, and that is a submatrix. So there will be thus 9 submatrix, out of which only 3 are principal submatrix, and out of which only this A11 is the leading principal submatrix. You try at home. Similarly, of the second order submatrix, we will be having these 9 submatrix of second order, out of which these 3 are the principal submatrix, out of which only this one is the leading principal submatrix. And in case of third order, this matrix itself is a submatrix, that is itself is a principal submatrix, that itself is a leading principal submatrix. So this is the difference between submatrix S, principal submatrix PS, and leading principal submatrix LPS. So the difference is that in case of submatrix, we have to delete any rows, any column. In principal submatrix, any rows, but the corresponding column we have to delete. But in leading principal submatrix, last row, last column. Okay. So in this particular case, the gradient vector is equal to 0. So it is optimal point or stationary point. Hessian matrix is 74, 20, 20, 34. It is a 2 by 2 matrix. And this is a square matrix, also a symmetric matrix. So this can be positive definite, provided all its leading principal minor is strictly positive. So it has 2 leading principal minor. One is of order 1, another is order 2. So LPS of first order will be this 74. And second order will be 74, 20, 20, 34. There is no third order here because maximum we can go up to 2 order because Hessian matrix is 2 by 2 matrix. Now corresponding minor will be 74, the determinant is 74. But 74, 20, 20, 34, the determinant will be 74 into 34 minus 20 into 20. So this is 2516 minus 400 will be 2116. So 74 is also strictly positive. 2116 is also strictly positive. So you can say that this Hessian matrix del square F del F at 32 is positive definite. So thereby the solution 32 is a minimum point. That means the objective function F will have minimum value at the point 32. And this minimum value will be how much? How much it will be? Minimum value? Yes, put these values. So this is x1. So 3 square is 9 plus x2 is 2. So 9 plus 2 is 11. 11 minus 11 is 0. 0 square is 0. Plus x1 is 3 plus x2 is 2, 2 square is 4, 4 plus 3 is 7, 7 minus 7 is 0. So 0 square will be 0. So 0 plus 0 is 0. So minimum value will be 0. You take any other value, x1 or x2, inside the bracket will not be 0. Either it will be some positive number or negative number. Square of that will be a positive number. Similarly, the second part also will be a positive number. So positive number plus positive number will get some positive number which is more than 0. So the 0 is the minimum value and that occurs at 3, 2. So this is the optimal solutions. So this is the way we can solve it analytically, whether a solution is optimal or not. Now let us discuss about the algorithm, that is numerical method, how we can solve a multivariable problem. So analytical solution, the procedure, any doubt? Please ask. Otherwise, we'll go to numerical method. That is, we will discuss Hook-Gibbs pattern search method. Yes, any doubt on numerical method? Analytical method? The gradient vector, Hessian matrix.
No, sir, but I
Okay.
think, I mean, it will be much more, clear for me if we can practice it on real life problem.
Yes. Okay. So this is a fundamental that you try to now you understand. When you apply in the real life practice, it will be more useful. So I have explained it through a very simple example so that it will be easier for you to understand, right? Okay. Now let us go to numerical method. Hook-Gibbs pattern search method. So this is applicable for a multivariable problem. There is number of unknown variable is more than 1. So here we will be searching in n linearly independent search directions. Thereby, we will search in the entire search space and find out the optimal point. And here we can start search from any arbitrary point. Arbitrarily, we select a point in the search domain, and from there, we will move from one point to another till we reach the optimal solution. So this is a point-to-point search. In every iterations, we'll be making two types of move. First, these moves are exploratory move. We explore wherever you are there in the current point, around the current point means the solutions. That is, in the neighborhood of the current point, we explore for if there is any better solution is available or not. Better solution means whether the function value at any point near to the current point is less. So that we have to search for, because our objective is to minimize. But in the pattern move, what we do, we establish corresponding to the previous point and the current point, we'll try some sort of coordinates different, and also the directions. That means how we have moved from the previous point to this point, in which directions actually the search direction is there, we get a somewhat idea, and in that direction we'll continue our search and jump from to the next point. So that's why you are jumping from one region to another region. So thereby the objective is to this pattern move actually it search in the entire search domain. So you can get a global solutions, right? And exploratory, we confine our search in the neighborhood, in the locality of the current point. So by mixing both exploratory move and this pattern move, we will be able to effectively find out the optimal solutions. Okay. Now, how does this exploratory moves works? So whenever you search it in the neighborhood of the current point, let's say the current point is C, defined by the coordinate, corresponding point is C1, C2 up to Cn, and the ith coordinate is, let's say, Ci. Okay. So in this vicinity, we'll be searching for a better solutions. So whenever you search, we have to decide our step size from the current point at what location we'll be searching for the next point. So the step size may vary from direction to direction. So let's say in the ith direction, the step size is del I. So del I, so correspondingly, this will be del 1, del 2, del I, then up to del n. And these individual directions, the step size may be same or may be different. So this again a vector. this del vector consists of the step size in n different directions. So delta 1 may be equal to delta 2, may be equal to delta 3, all may be same or may be different. There is up to we to decide. Okay. So what you do, whenever you search in any directions, we take one step ahead, 1 point, and one step back, another point. So thus we'll have 3 points. The current point, this is the current point Ci. Suppose you are searching the ith direction, and ith direction is, let's say, the horizontal directions. Let's say it is a x1 directions, right? That is a horizontal directions. So we let's say in the horizontal direction, the step size is del I. So we will be at Ci plus delta I. So this will be the another point. That is a one step forward. Then from the current point, we take one step backward. So Ci minus delta I. So in these directions, all other coordinate value will remain same. Only the coordinate of this ith coordinate is only vary. So at the current point, it will be Ci, the ith coordinate. And at this point, the ith coordinate will be Ci plus delta I. And at this point, the ith coordinate will be Ci minus delta I. Then at these 3 points, we'll find out the function value, right? So let's say at the current point, f of Ci, let's say it is f. And at this point, there is at the forward point, let's say the corresponding function value is f plus, and at the back point, the corresponding function value is, let's say, f minus. So we will be comparing these 3 function value, f minus, f and f plus. Whichever is the best. Best means, because our objective is to minimize. So out of these 3 value, whichever is minimum, we will be moving to that point. And from that point, again, that is taken a base point, we'll search in the next directions. So like that, one after another, in all n direction, we will be searching, and finally we'll be landing off with a better point. So this is explore. We explore in both positive and negative directions in one particular directions. In any coordinate directions, both positive and negative, move forward and backward. At 3 points, we'll compare the f value and we move wherever the value is minimum. So in step 1, the algorithm goes like this. In step 1, we set the iteration counter I is equal to 1, and the x vector is equal to c vector c, that is the current point. So at 3 different points, we evaluate the function values, and then we find the minimum of these 3, let's say f minimum. So we move to that point. So f of x is equal to f minimum. Then this step 1, 2, 3, we repeat it for all other coordinate directions. So I is equal to 1. So long as I is less than capital N, because we have n unknown variable, we keep on repeating from step 1 to 4. And when one direction is over, we set I is equal to I plus 1, and so long as it is less than capital N, we go to step 2 and continue from 2 to 4. Once we reach n, then the exploratory move is completed. When we have searched in all the n directions, and then let's say we are at the current point, whatever the output means after the end of the exploratory move, after searching in n different directions, wherever you are there, if that is different than the point at which we have started our exploratory move, that is C. So current point, if it is different than the point at which we have started the exploratory move, then we can say that we have explored and we got a better solutions. So that is a exploratory move which we call it success. But if you do not find any new solutions and you are still, even after searching in n directions, your current point is still at the C, means x is equal to C, then we can say we searched in L different direction, but we did not find any better solutions. So then we call that exploratory move is a failure. Then in the pattern move, what you do, in the current point, let's say xk, vector, then to the power, this is not actually to the power, we say at the, within the plain bracket, if you write k means at the kth iterations. What is that? The value of x vector, that is solution vector. So previous iterations k minus 1, the solution vector was x. So what you do, you just join this previous point with the current point, and that draw a line from the previous point to the current point, and then we extrapolate it, we extend that point in the same directions, and then we jump by whatever this magnitude is there, xk minus xk1, by that amount we jump in the same direction. Wherever you land there, that will be your next point. There is k plus 1th point, but under pattern move, so xp. So under pattern move, we, from the current point xk, we move to xk plus 1 under pattern move, so p. So this will be current point xk plus we jump by this amount, that is distance from the previous point to the current point, that is xk minus 1. And since it is a vector, this minus means in the same directions. It is nothing but joining a line from the previous point to the current point. Whatever in that directions, we have to jump it. And the magnitude is decided by this magnitude of this vector subtraction, xk minus 1. Okay, now let us write down the algorithm for this Hook-Gibbs pattern search. So step 1 will be initializations. So here for the first part, in step 1 will be all the assumptions. That is, you have to assume the initial solutions, that is x0, means at the 0th iterations, and this we have to select arbitrarily. Also, you have to select the step size, that values, that vector delta. So delta 1, delta 2, up to del n. In different direction, what is the step size? So this is a vector called increment vector or step vector. Then we have to, if exploratory move is a failure, that means we are not finding anywhere in the neighborhood any better solution, means the optimal point is even closer to the existing point. So that's why we have to reduce this step size. So that's a step reduction factor. We have to assume alpha, which is more than 1. So if you want to reduce it by step size by half, then the step reduction factor alpha will be equal to 2. That means del will be is equal to del by 2, means reduced by half. Then you have to specify your desired accuracies. There is maximum permissible error, epsilon. There is very small number, positive number, 0 plus. So this is used for the termination. Till that time, you go on searching, because your accuracy, the solution accuracy has not yet reached. The next is iteration counter is set to 0, k is equal to 0. Step 2. In the first iterations, since we do not have the previous point, so we cannot establish a pattern. So in the first iteration, there is no pattern move. We straight away go to the exploratory move. So do exploratory move around this x0. So in general, it is xk. Now k is 0. So now you are x0, and around that you find out do a exploratory move. And let's say the outcome of exploratory move is x. So if x is different than x0, this is a success. But if x is equal to x0, then you call it this is a failure. Okay. So if exploratory move is a success, that means the output point x is not same as the input point, that is xk. Initially it is x0, k is 0. Then we set that the next point xk plus 1 is equal to this current point x. So whatever the new point is a success point, better point, so that we accept as the new point. So xk plus 1 will be x. And then we'll go to step 4. Otherwise, we'll go to step 3. So what you do in step 3? Step 3 is actually check for the termination, whether time has come to stop the algorithm and write down the answer. Okay. So here we'll check whether this step vector, that size, has been reduced to a sufficiently lowest magnitude. And what is that magnitude? Even it is less than our maximum permissible error, then we say that our solution we have achieved to the desired accuracy will stop and write down whatever that current point, at that point, kth point is your minimum point. So here we are writing not 1 bar on either side, we are writing 2 bar on either side. So anyone, what is this 2 bar on either side? Are you aware of this 2 bar on either side? Am I audible?
Yes, sir.
Hello? Are you aware of this 2 bar on the other side? Hello? Anyone? Someone please respond if I am connected or disconnected.
So you are there. We are audible.
Audible. Okay, so do you know this? What is this 2 bar on either side? Yes or no? Tell me. Hello?
No, sir. Right now
Okay.
I am traveling.
Okay. So let me explain then. Okay. So this 2 bar on either side is applicable whenever it is a vector, right? Had it been a number or a scalar quantity, the corresponding parameter would be the absolute value. But here it is not a number, it is a vector. So for a vector corresponding absolute value, the proper parameter, the operator is called norm, N-O-R-M. So this is norm of the step vector. So norm means what? If a vector is equal to, let's say, x1, x2, right? If a vector is x1, x2, so norm of that vector will be what? Square root of x1 square plus x2 square. Okay. So that will be a number. And if the number is less than your epsilon, then we say that we stop and let us print that this xk is your minimum value, that minimum point. Otherwise, we have to reduce this gradient vector, this which is step vector. So delta, each of these delta 1, delta 2, delta 3 will be reduced by half, not by alpha. So alpha, if it is 2, it is reduced by half. So for all these direction, 1 to n, we have to reduce it. And then you have to go to step 2. Step 4, after doing this one, we go to step 4. In step 4, we actually do the pattern move, right? So before doing this pattern move, we set k is equal to k plus 1. And then next point under pattern move, after the pattern move, for the next point would be this. By using this formula, we'll be getting the pattern move. Next point under pattern move. Current point plus the distance from the previous point. Now in the step 5, after the always you note it, in every iterations, after pattern move, you have to do the exploratory move. Except which iteration? The first iterations. Because in the first iterations, we do not have any previous point. So we cannot do any pattern move because we cannot establish any pattern of movement. Okay. So do EM at this, after this pattern move, wherever you reach, there is XP k plus 1. Around that, you do one exploratory move. And let the outcome be xk plus 1. Then now you compare whatever that xk plus 1 point you got and the previous point was xk. At these 2 points, you compare their function values and check whether the next point is superior than the current point. Superior means the function value is less than that of the previous point. If it is less, then we move it to the next point, that is xk plus 1. So from xk plus 1, we do again a pattern move, then a exploratory move, next iterations. So go to step 4 to do the next iterations, starting with pattern move followed by exploratory move. Otherwise, if this is not a superior point, better point, you go back to step 3. Check for termination check. Otherwise, you reduce that. Which one? In step 3, what is there? Step 3 is the check for termination. So you reduce this. If this step vector is less, stop. Otherwise, you reduce it and then go to step 2 and do the exploratory move. Okay. So that 6 steps algorithm. Yes, this 6 steps algorithm, let us try to understand through a numerical example. So objective is to minimize the same Himmel-Blau function. Very simple example, let us take it so that it will be easier to understand. Using Hook-Gibbs pattern search method. And here let us assume that the starting point is 0, 0. That is x1, 0, x2, 0. We have two unknown variables, x1 and x2, and that is x0. At the 0th iterations, the solution is 0, 0. And increment vector del is 0.5, 0.5. That means in the x1 direction also step size is 0.5. In x2 direction also step size is 0.5. And step reduction factor, that is alpha is equal to half, means we'll be reducing the step vector by half. And the desired accuracy, let's say it is epsilon is equal to 0.1, means we require 1 decimal point accuracy. Let us solve it. So in step 1, let us denote vector x0 at the 0th iteration is equal to 0, 0. I have written in transpose, means it is actually a column vector x0. And vector del is 0.5, 0.5. Alpha is 2, epsilon is 0.1, and set iteration counter k is equal to 0. Okay, this is step 1. In step 2, we begin the movement. But since it is the first iterations, no pattern move straight away because we do not have any previous point. So straight away we do one exploratory move. So let us do it. Exploratory move. So we have to search in 2 directions. First x1 direction, then x2 direction. When you search in x1 direction, when you move in x1 direction, there is a horizontal line. The x2 coordinate remains constant, and x2 coordinate was at 0, so x2 remains constant at 0. We only vary the x1 value. So at the current point, x1 will be 0. One step ahead point, the x1 coordinate will be 0 plus 0.5. That will be 0.5 plus 0.5. And one step back, if you go, the x1 coordinate at that point will be 0 minus 0.5, so it will be minus 0.5. And at all the 3 points, these are all the the values of x1 coordinate. And x2 coordinate will be 0 at each of these 3 points. So thereby, the current point will be 0, 0. Ahead point will be 0.5, 0. Behind point will be minus 0.5, 0. So let us find out the function value at these 3 points. Evaluate f values at these 3 points. So let us find out f means at the current point, f at 0, 0. So let us put it. So x1 0, x2 0 minus 11 square. So it will be 11 square is 121. Then x1 0, x2 0 minus 7. So minus 7 is 49. So 121 plus 49 will be 170. Right? Now forward point, f plus. So this is x1 is 0.5, x2 is still at 0. So let us put, so x1 square, so this is 0.5 square plus x2 is 0 minus 11. So 11, 0.5 square, there is 0.25 minus 11 whole square. Plus x1 is 0.5 plus x2 square, there is 0 minus 7. So when you simplify it, you'll be getting a value 157.81. Let us find out the corresponding value at the behind point. So x1 is minus 0.5, x2 is 0. So x1 square, so minus 0.5 square plus x2, there is 0, minus 11 whole square, plus x1 is minus 0.5 plus x2 square is 0, minus 7 whole square. So if you calculate, you will get 171.81. So we get 3 function values. Which is the best values here? Out of these 3, whichever is minimum, because our objective is to minimize. So minimum value is 157.81. So therefore, we will move to this forward point, that is 0.5, 0. Because compared to 170, or will not even prefer the behind point, there the even value which is increasing. So compared to these 3 locations in x1 directions, the best value we obtain is a forward point, that is f plus, that occurs at 0.5, 0, having a corresponding function value 157.81. So we have finished the search in x1 direction. Now from this point, then we will do the x2. We will do the search in the x2 directions. So minimum is 157.81. So we move from current point is 0, 0 to 0.5, 0. Then from this 0.5, 0, we will search along x2 directions. We will vary only x2, but keeping x1, which is equal to 0.5, constant. So one step upward, if the x2 direction is a vertical line, so one step upward, one step downward, we have to take it. Let us do it. So keeping x1 is equal to 0.5 constant. So current point, already we have found out the corresponding f value, that is 157.81, that is at 0.5, 0. Let us take one step ahead, that is upward. So x1 will be at 0.5, but x2 value will be 0 plus 0.5, so that is 0.5. So let us find out corresponding function value. You check it. It will be 144.13. x1 square, so 0.5 square, plus x2 0.5 minus 11 whole square, plus x1 is 0.5 plus x2 square, 0.5 square minus 7 whole square. You will get 144.13. Now let us take one step behind. So here, since it is a vertical directions, x2 directions, so we will be going downwards. There is, and whatever the value will get, that will f minus. F minus will be x1 remains constant 0.5, but x2 will be 0 minus 0.5. So it will be minus 0.5. So let us put these values. If you put it, we will get 165.63. Let us now compare these 3 values: 157.81, 144.13, and 165.63. Minimum is 144.13. So this is occurring at the upward point, up point, that is at 0.5, 0.5. So we'll move from 0.5, 0 to 0.5, 0.5. So this is the outcome of exploratory move in all the directions. All the direction means there will be only 2 directions, because we have 2 unknown variables. First we search in x1 directions, then we search in x2 directions, and we landed at a new point, that is 0.5, 0.5. We started the exploratory move from 0, 0. So this is a different from 0, 0. So we can call it that we succeeded the exploratory move. We got a better solutions. At 0, 0, it was 170, but at 0.5, 0.5, we are getting the function value 144.13, which is less than the 170. Any doubt? How we are doing exploratory move? X1 direction first, then x2 directions. We compare the function values at 3 points: current point, ahead point, and behind point. one step forward, one step backward. Okay. So now, since it is a better solutions, we actually move to this new point. So this new point will be x1. So x0 was 0, 0. Now this, at the end of the exploratory move, we are at 0.5, 0.5. So this will be our x1. Right. Now what is to be done? We have to do the pattern move. So for the pattern move, this is the formula shown in the blue color. xp k plus 1 is equal to current point xk plus the distance from the previous point, the xk minus xk minus 1. So at present, the k is equal to 1 because we have moved to next point x1. So we updated k value, k is equal to k plus 1. So 0 plus 1 is equal to 1. So now let us put k is equal to 1 here in this expression. So we get xp 1 plus 1. So that is xp2 on the left hand side is equal to x1 plus x1 minus x0. So that means x1 plus x1 2x1 minus x0. Well, let us put the value. So 2 into what is x1? x1 is 0.5, 0.5. So let us write down 0.5, 0.5 minus x0, x0 is 0, 0. So this is a matrix. So 2 into this matrix will be 2 into 0.5 is equal to 1 and 2 into 0.5 will be 1. So this matrix will be 1, 1 matrix. Now 1, 1 minus 0, 0 will be 1 minus 0, 1, 1 minus 0, 1. So thus we reached after the pattern move a point that is 1, 1 where x1 coordinate is 1, x2 coordinate is 1. So this is for the next iteration, there is second iterations, but after the pattern move. But second iteration will be completed, followed by one exploratory move. So that point will be x2, right? So this 1, 1 is xp2, under 2, just after pattern move. After pattern move, we have to do one exploratory move. Let us do that. So from 1, 1, let us now do one exploratory move. So from 1, 1 again, let us move first along the x1, then along the x2. Okay. So when you move along x1, the x2 coordinate 1 is kept constant. So that's why see all the 3 point x2 coordinate is 1, 1, 1. And we only vary the x1 coordinate. So for the forward point, it will be 1 plus 0.5, it is 1.5. And for the backward point, it will be 1 minus 0.5, it is 0.5. So let us find out the corresponding f value. So at 1, 1, the function value is 106. You can check it, putting that in the Himal-Blau function, put x1 is equal to 1, x2 is equal to 1. When you calculate, you will get 106. Then at 1.5, 1, the function value you will get 80.31. At the behind point, there is 0.5, 1, the function value will be 125.31. So we got 3 values shown in the blue color. Find out the minimum value. So the minimum value is 80.31. So we move to the point, corresponding point, there is 1.5, 1. So from 1, 1, we move to 1.5, 1. That is after searching in x1 direction. But this is not complete exploratory move because we have searched along only one direction. But we have to do now in the second direction because we have 2 unknown variables. So we have to search in both the directions. So now let us move now from 1.5, 1, search along x2 directions. So along x2 direction from 1.5, 1 means x2 will remain same. No, sorry, x1 will remain same. So the 1.5, 1.5, 1.5, but x2 values will now change. So for the current point, it will be 1. For the upward point, there is f plus. To get f plus, it will be 1 plus 0.5 will be 1.5. and for the downward point will be 1 minus 0.5 will be 0.5. So let us find out the corresponding f value. So f, that is at 1.5 comma 1, it will be 80.31, as already you have found out earlier. Now at upward point f plus, that is f 1.5 comma 1.5, the function value will get 63.13. Similarly, at the downward point, that is 1.5 comma 0.5, that is function value is f minus, you calculate, you will get 95.63. Again, let us compare. So the minimum value out of these three is 63.13. Corresponding point is 1.5 comma 1.5. So we have to move to this point. So from current point 1.5 comma 1, we will move to 1.5 comma 1.5. And since this point is different from that starting point before exploratory move, that is 1, 1, so exploratory move is a success. 1.5 comma 1.5 is not same as 1, 1. This is 1. We were at 1, 1 just before exploratory move, that is just after pattern move. And after exploratory move, we reach to 1.5 comma 1.5. And we move to this point. So this 1.5 comma 1.5 completes your second movement for the second iteration. So this will be x2. Now we have to compare that function value at x2 and the previous point is x1. Function value at x1, is it really less than, is it really better? That you have to check it. Because just after pattern move, we have not checked the corresponding function value, right? So we need to check it here. We have to compare the function value between x1 and x2. Let us compare. So that is your step 6. So f at x2, we have calculated, that is 63.125. And f at x1, that is 0.5 comma 0.5. x1 is just before pattern move, 0.5 comma 0.5. It was 144.125. So compared to x1 at x2, the function value is improving, means it is less, because 63.125 at x2 is less than 144.125 that is at x1. So that's why we gladly accept this x2, because we are getting a better solutions. We accept this and then go to step 4 to do the next set of movement, that is pattern move followed by exploratory move. If this is not less, then we will not accept this. This x2 will not accept and will again come back to the x1. Okay. So now again you have to do the pattern move. So now the k value is updated to k plus 1. So the 1 plus 1, it is 2. So now let us do the pattern move. Means at this formula, let us put k equal to 2. So we'll be getting xp3. So xp3 will be equal to x2 plus x2 minus x1. So this is 2x2 minus x1. And x2 value was how much? 1.5 comma 1.5. And x1 was 0.5 comma 0.5. Okay. So 2 into this will get 3. The 1.5 into 2 is 3. So it will be 3 minus 0.5 comma 0.5. So we will be getting 2.5 comma 2.5. This is XP in third iterations. And at XP3, we are not checking its function value. We will be going straight away the exploratory move. Because always we have to do a exploratory move just after the pattern move. Exception is only in the first case, first iteration, because in first iteration we have only exploratory move, no pattern move, because we had no previous point to establish any pattern. Okay, so now we are at 2.5, 2.5 in the third iteration after the pattern move. And now we have to do what? Exploratory move. Let us do. Similarly, 2.5, 2.5, the current point, function value is 8.13. Then along x1, no? So x1 is 2.5, that will vary, but x2, 2.5 will keep it constant for all the 3 points. Okay. So forward point, it will be 2.5 plus 0.5, it is 3 here. And behind point, 2.5 minus 0.5, it will be 2. So at forward point 3, 2.5, the function value you check, you will get 5.31. Then let us find out for the behind point, that is 2, 2.5, that is f minus, that is equal to 21.81. Let us compare these three values, function values. Minimum is 5.31. So we move from 2.5, 2.5 to 3, 2.5. That is the result of searching along x1 directions. Now from this point, 3, 2.5 will search in the x2 direction. So x2 means which coordinate will keep constant? X1. X1 is how much? 3. So for all the 3 points, the x1 will be 3. Will vary only x2 values, that is 2.5. So x2 value 2.5. So forward point will be 2.5 plus 0.5 will be 3. And backward point will be 2.5 minus 0.5, it will be 2. So we have now 3 points. The current point is 3, 2.5. Function value will be 5.31. Upward point, it will be 3, 3. Corresponding f value will be 26. Then down point, there is 3, 2, 3, 2. Corresponding function value is 0. Let us compare now. 5.31, 26 and 0. So minimum value is 0. So we move to 3, 2, 3, 2 from 3.3, 2.5. So thus, after the exploratory move, we are at the point 3, 2, which is different from the point that is just before we started the exploratory move, there is 2.5, 2.5. So this is a success. So we move there. So this 3, 2 will be the x3. So xp3 was 2.5, 2.5, and as per exploratory move, we move to a new point that is 3, 2. So this is x3. Now what is to be done? After the exploratory move, wherever you are there, at that point, whatever f value is there, you have to compare with the previous point f value. So previous point was x2, and x2 coordinate was 1.5, 1.5, not 2.5, 2.5. 2.5, 2.5 is the xp3 after the pattern move, right? That is that is x2 was 1.5, 1.5. From here we have jumped and we have done a pattern move to reach xp3, that is 2.5, 2.5. Okay. So now let us compare the function value at x3 and x2. x3 means 3, 2. x2 means 1.5, 1.5. So 0 at x3 we got 0. At x2 it is 63.125. So function value is reduced. So we are happy. We accept it. And then we proceed further. So proceed further means what? Again you do next set of movement, next iterations. So again a pattern move. We go to xp4, then do a exploratory move to reach to x4. And then you compare function value at x4 with the x3. So at x3, we are getting 0, right? Now let us see at x4, are you getting a value less than 0? When it's negative value, will you get? Let us check. If you are not getting a negative value, means we are not reducing further. So we have to again go back. We cannot proceed further. We cannot go to step 4 because this may not be satisfied. Let us check. Okay. So now step 4, k is equal to k plus 1. So now k is equal to 2 plus 1, that is 3. So put it in this pattern move formula. So now left hand side will be xp 3 plus 1. K plus 1 is 3 plus 1, then xp 4. So xp4 will be equal to x3 plus x3 minus x2. That is equal to twice x3 minus x2. And x3 is what? 3, 2. So 3, 2 into 2 minus x2. x2 was what? 1.5, 1.5. Okay. So 3, 2 multiplied with 2 will get 6, 4 minus 1.5, 1.5. So we will be getting 4.5, 2.5. So this is after the pattern move in the 4th iterations. So this is xp4. Then what to do? We do an exploratory move. And wherever you reach after the exploratory move, that will be x4. Then we'll compare x4 with x3. Like that. We have to do it. So let us do now exploratory move from 4.5, 2.5. Okay. So similarly here that x2 value kept constant 2.5 and x1 values at the current one it is 4.5, forward point it is 4.5 plus 0.5 it is 5, and behind point 4.5 minus 0.5 it is 4. So corresponding the function value is 152.13, 290.31, 66.81. So which is minimum? 66.81 is minimum. So we have to move to this f minus point, that is backward point, 34, 2.5. Right? Now let us search along x2 directions. So x1 value remains same at 4 and x2 will be 2.5, 3 and 2. So we get corresponding f value 66.81, 150. So minimum is 50. So we move to 4.2. Right? So this 4.2 is our x4. Now let us compare with at x3, what was the function value? The previous point. So at previous point x3, function value was 0. But at the current point x4, there is 4, 2, function value is 50. So it is no longer less. Now it has started increasing. So this is not a better point. So we cannot accept this x4. Right? So we cannot proceed further to do the next iteration of movement, that is pattern move and exploratory move, pattern move plus exploratory move. Rather, now for the first time, we have to go back to step 3. Otherwise, in the previous one, whatever we are doing, we are going to step 4 because we were getting that at the new point, what the function value was better than the function value at the previous point. But this is the first time we are getting a case where at the new point, the function value is not better. It is not less, right? 50 is not less than 0. Is that clear? So in step 3, what do we do? We check whether the time has come for the termination check. So let us find out now the norm of this vector. There is the step vector. Is it less than 0.1? There is epsilon. Let us check. Now, norm of a vector is that if x is a vector having coordinate x1, x2 up to xn, please correct it. This is x2, x1, x2. Let me correct it. So this is not x1, x1, rather this is x1, x2. Okay. So this was a mistake. Then its norm is denoted as x, vector x with a 2 double bar on either side, and is defined as the norm of a vector x is the square root of x1 square plus x2 square till plus up to xn square. So this norm represents actually the Euclidean length. Suppose the vector x is 1, 2, means x1 is 1 and x2 is 2. Then norm of vector x will be what? 1 square plus 2 square. This will be 5 root over of 5, then 2.236. If you are using MATLAB, then the corresponding subroutine to find norm is NORM. So you can enter the vector x is equal to this matrix, that is 1, 2. So it is a vector. And simply if you write the command norm within bracket x, it will give you the result. So now let us check it. So in this case, the step vector is 0.5, 0.5. So its norm would be 0.5 square plus 0.5 square square root. So that will be 0.707. It is not less than 0.1. So we cannot stop. We have to continue. So when you continue, we have to now reduce this step vector. So new step vector will be current step vector divided by 2. So this is 0.5, 0.5 divided by 2. So thereby it will be 0.25, 0.25. So now the step size in the exploratory move will not be plus or minus 0.5. Rather now it will be plus or minus 0.25. So let us do that. Go to step 2. Do exploratory move with what? 3, 2 as the base point, because we again come back to the better point, because at 3, 2 our function values were 0. We did not accept that x4, because at x4 the function value was more, that is inferior. So that's why we did not accept, we reject that x4 and we have come back to the x3, the just previous point. So this is taken as a base point, and then we have to do the exploratory move. So let us do it around x3, a3, 2. So along x1, so x2 is 2 kept constant. So now here at the forward point, it is 3 plus not 0.5, no, it will be 0.25. So x1 will be 3.25, and at the behind point, it will be 2.75. 3 minus 0.25. So it will be 2.75. Find out the function value. So it is at current point it is 0, and other 2 point will be 2.5, 2.13. You see here when you compare, the minimum point is 0. That is at 3, 2 only. So we do not move to any other point. We remain at 3, 2. With other points where are not superior. Function value we are not getting less. So we remain at 3, 2. Now let us search in x2 directions. So x2 direction means x1, that is 3 remains constant. Let us change x2. So 2 plus 0.25 is 2.25, and 2 minus 0.25 will be 1.75. So the function value will be 0, 1.19, 0.94. So 3 values. Again minimum is 0, that is at 3, 2. So we remain at 3, 2 only. So even if we did a exploratory move, but after the exploratory move also we did not reach to any new point. We are at 3.2. After exploratory move also we are at 3.2. So it is a failure. We did not get any new point. So since it is a failure, we have to go to step 3. So we have to check whether time has come to terminate. So let us check for the norm. So norm of the current step vector. So now the current step vector is not 0.5, 0.5, it is 0.25, 0.25. So 0.25 square plus 0.25 square root of that will get 0.3536. Not less than 0.1. So we cannot stop. We have to still reduce our step vector. So again, del is equal to delta by 2. So it will be 0.25 divided by 2, it will be 0.125, 0.125. So go to step 2 and do exploratory move with step size 0.125, 0.125. So here also you see that the 3 values that you get by changing along x1 directions, keeping x2 constant. x2 is 2, it has kept constant. Only we have varied x1. So the minimum value will be at 0 only. So we cannot move any new point. We remain at 3, 2. Let us search along x2 direction. Even after x2 direction you move it, you'll find again the minimum value will be 0. That is at 3, 2. So we remain at 3, 2. So again the EM will be a failure. Explorative move, we are not getting any new point. So we again go to step 3. Find out again the norm. So here 0.125 square plus 0.12 square divided by square root. We'll get 0.1768. Still it is not less than 0.1. So proceed. Again reduce by half. So now the step vector will be 0.0625, 0.0625. Let us do one more exploratory move about 3, 2. Along x1 directions. Again we find what? The function value minimum is at 0. So we remain at 3, 2. This blue color, the values 0, 0.1475, 0.1416 are the 3 function values. So minimum is again 0. Let us search along x2 directions. So here also the 3 function value you'll see 0, 0.0799, 0.0645. Again it is 0. So we remain at 3, 2. So again exploratory move is a failure. Go to step 3. Let us find out now norm. Now we find the norm is 0.0625 square plus 0.0625 square root of this is 0.0884. For the first time we get that norm is less than our epsilon value, that is 0.1. So we now stop. Algorithm stops here and we write down our output result that the minimum point is the 3, 2 only. This is the way the Hooks-Gibbs algorithm works. And finally, it searches out the optimal point. Now, this is that calculation that we have done it. Initially, we had 0, 0, x1, 0, x2, 0, and k value, the iteration counter was set to 0. So this 0, 0 was x0, right? And corresponding function value was 170. Then we do one exploratory move. This is a summary sheet of whatever that calculation we have done it. So we moved along, search along x1 directions. So we moved to 0.5, 0. Then we search along x2 directions and we move to 0.5, 0.5. Right? And this point is your x1 point. And at this x1 point, function value is 144.125, which is less than 170. So we accept it. So k is equal to 1. Then you do the second iteration. In the second iteration, first we do pattern move. And then we do exploratory move. And then we reach to point 2. Right. So from x1, first we go to xp2 and then x2. Similarly, from x2 to x3, we go via pattern move. So from x2, first we do pattern move, we reach to xp3. Then we do exploratory move, x1, x2, then we reach x3. Then next, we reach to xp4 and then x4. And accordingly, at x0, function value was 170. At x1, function value was 144, reducing. So we accept it. Then compared to x1 and x2, we do not compare the function value of xp2 with x1. No. We straightaway do, after pattern move, we do exploratory move, we reach to x2. We compare x2 with x1. So 63.125 is less than 144.125. So we accept it. Then we do xp3, then x3. Then this x3 function value is 0. And this is less than 63.125. So you accept it gladly. From x3, then we do another iteration move. So xp4, then x4. But at x4, it is 50, started increasing. So this 50 is no longer less than 0. So we cannot proceed. We cannot accept this x4. Again, we go back to x3. And this around this x3, that is where it is function 0, we are searching for the closure and closure around this x3 point. But we did not get any other better point. And this x3 itself is the what? The optimal solutions. And these are the corresponding coordinate x1, x2. Okay, so x1 is 0.5, 0.5. Then we jump by pattern move. We reach to 1, 1. Then we do exploratory move. So then we move to 1.5, 1 after searching in x1 direction. Then we move to searching in the x2 direction. We reach to 1.5, 1.5. This is your x2. Then we did pattern move, reach to 2.5, 2.5. There is xp3. Then we do exploratory move. So exploratory move, two components. After x1, we reach to 3, 2.5. After x2, we reach to 3. This is your x3, right? So this is the summary sheet of whatever the movement that we have done it. And the last column gives us the functional values. So graphically, whatever we have done it tabular form, this is the graphically one. See here, earlier we are at x0, there is 0, 0, x0, 0, 0. We moved horizontally forward. So this is 0.5, 0, x1 direction. Then x2 directions, we go upward. We reached at 0.5, 0.5. So this is the end of the first exploratory move. So we reached at x1. From x0 to x1. In these first iterations, there is no pattern move because we did not have any x minus 1 to establish any pattern. Now from we got x0 and x1, two consecutive points we got it. What we did, we joined this x0 to x1 and then we extended the same direction such that the distance from x1 to x0, whatever is there, this diagonal from x0 to x1 is equal to this diagonal x1 to x2. So wherever it is there, this is your xp2. From xp2, we did x1, then x2, we reached to x2. From x2, again, we joined x1. We compared x2 to x1. So join x1 to x2 in the same direction. Sorry. We have proceeded from x1 to, you just take a scale and from x1 to x2 you join and proceed, same directions you proceed. And the length from xp3 to x2 will be equal to x2 to x1. Whatever length from x1 to x2 is there, the same length will be from x2 to xp. So we are jumping from x2 by equal equal distance. From xp3, again x1 direction, then x2 directions, and then we, this is xp3. So this is your x3. Now compared to x3 to x2, the corresponding value is less, we accept it. So from x3, we jump. From we join x2 to x3, x2 to x3 join, and in the same direction we jump like this. This is xp4. Then x1 direction, then x2 direction, this is x4. But at x4, this is value we are getting more. So we do not accept it, we return back to this x3. And around this x3, we search with the reduced step vector till we close around to this x3 and declare that this x3 is the minimum point itself. No other better point. No other better point around which will give you the function value less than 0. So this is the way the Fuchs-Gibbs pattern search method works. Any doubt? Fuchs-Gibbs pattern search? Okay, in the remaining time, let us discuss now in the MATLAB optimization toolbox. So in MATLAB optimization toolbox, it gives us the non-linear programming, it solves non-linear programming problem. So if it is a, whatever we discussed so far is unconstrained problem. But if there are constraints, then there will be a constraint optimization problem. For that, the subroutine is f min con. And in unconstrained, it is classified under two groups, single variable, multivariable. In single variable, the corresponding subroutine is f min bnd. That already we discussed in the last class. But in the multivariable case, we have two subroutines. One is f bin search. There is using this Fuchs-Gibbs search method, the direct search method, that corresponding subroutine is f min search. But if we use Cauchy's search method, which is gradient-based method, the corresponding subroutine is f min unc. So directly using from MATLAB optimization toolbox, we can also get the same result. So whatever that we got the result, if you use f min search, we'll get the same result. Let us see. So we have to invoke this optimization toolbox by clicking apps and then optimizations like this. First apps and then optimizations. So this is app min BND. This is single variable already we discussed in the last class. Let us. Then app min search. So this is for multivariable problem. So under solver you select app min search, unconstrained nonlinear minimization problem. In objective functions, write down @fg2. That means your objective function, all the operations, whatever you are going to do it, that you have to write down in a file called fg2.m. Starting point 0, 0. So this is, we have written 0, semicolon 0. That means this is a column vector, right? Semicolon means it is a next column. Within bracket, square bracket. And then press start, you will get the result. So see here, x1 is 3, x2 is 2. Same result will get it. Then if you are using the gradient based method, so you can use this app min UNC, and there also 0, 0, and same objective function fg2, press start, we will get the same result 3, 2. So this is the way we can use MATLAB optimization toolbox to solve multivariable optimization problem. And if it is a constraint one, then you have to use that app min con and you can solve it. So the same thing. You see here in FG2, I have written here, see, in FG2, we have to write down, because it calculates both function value as well as gradient vector, GF, it returns. FG2, it returns two values. One is function values. So these function values, F, see here, F is equal to P1 square plus P2 square, where P1 is this one, x1 square plus x2 minus 11, and P2 is the second term, x1 plus x2 square minus 7. So this gives us the function value. And for this gradient vector, it has two components. So GF1, GF2. GF1 will give you del f by del x1. So del f by del x1 is what? 4x1 plus whatever this term is your P1 plus 2 into P2. So that's why I written 4 into x1 into P1 plus 2 into P2. I have written this x1 square plus x2 minus 11 is the P1. See here, x1 square plus x2 minus 11. That is inside the bracket, whatever is there in the first term. Similarly, the second element, that is del f by del x2, is 2 into P1 plus 4x2 into P2. So 2 into P1 plus 4x2 into P2. So this is the way you have to write down your FG2. So with this, we complete your multivariable optimization problem. Both using first we learned about the analytical procedure, that is by taking gradient vector equal to 0, then Hessian matrix, and if it is positive definite, means it's both all the leading principal minor are strictly positive, then it will be called positive definite and we'll getting a minimum point. Then we discuss one numerical method, that is Hook-Schiff's method, how with by hand calculation we have understood the detailed step-by-step algorithm. And then also we learn that how we can use MATLAB optimization toolbox to solve this, both using that direct search method and also the gradient based method. Thank you. If you have any doubt, I can clarify. Otherwise, we will close this session. Any doubt? Otherwise, you can also, my video lectures are there. You can watch the video lecture. And if anytime any doubt is there, you can ask me. I will be happy to answer you.
Okay, thank you very much, sir.
Thank you.
Sir, your lecture is really quite excellent. And honestly speaking, sir, I'm quite astonished.
Okay.
I'm really quite glad to be in your class. Thank you very much, sir.
Thank you. Thank you. It's my pleasure to take your class. Thank you. Any doubt, please feel free to ask me. Yeah? Okay.
Sir, particularly the example that you have showed us, in those examples, I have not felt any kind of doubt. But the fact is that, sir, I need to actually use them for, my research work and my actually,
Yeah.
applications.
Yeah.
So, sir, on that regard, would you please be kind to suggest me some good books on optimization in MATLAB, like that sort of books, please?
In MATLAB?
Yes, sir.
Acha, in MATLAB, you can read this MATLAB manual, you can read it. Otherwise, in the help also it is given. Or you can, all these things in MATLAB, you can watch my video lecture also. MATLAB, that optimization toolbox, I have given 2 lectures or 3 lectures are there. You can watch that. In detail, you can know.
But sir, any particular book that you would love to suggest me?
Actually, textbook, I have not find out this regarding this MATLAB optimization toolbox. Their manual, you can see it, right? And MATLAB coding, that for the single variable problem, you can find in my book, that MATLAB book.
Okay. Basically, sir, I'm not an engineer. I'm a management.
No problem. Even if you are not an engineer, no problem. If you can understand this, all these things, the arithmetic operations, derivative, all these things, we'll be able to do it. No problem.
Actually, sir, I'm working in the field of finance, so I need to use this thing for finance and economics.
Okay.
And for MATLAB, actually, I have followed the book written by Stephen C. Chapra, sir.
Okay.
Applied numerical methods with MATLAB.
Okay.
In that particular book, actually, sir has written very few chapters on optimization. So that is why I am requesting you humbly that it would be very kind of, if please be kind to suggest me some books which is dedicated, only through optimization. Optimization through MATLAB. Okay, it will be really, really very, great for me to be precise.
Okay, you can. I'll let you know if I get such books. Actually, I have not seen any textbook where all these things MATLAB is there.
Okay. Thank you very much, sir. Thank you very much. So I will be in your touch through email and WhatsApp.
Sure. Most welcome.
Thank you very much, sir.
So, madam.
Sir. Yes, sir. Thank you, sir.
Is there any doubts I can clarify? Otherwise,
I think no doubt, sir.
okay, then all the participants, thank you very much.
Thank you, sir. Thank you.
And wish you all the best. If you have any other doubts anytime, please feel free to contact me. Okay.
Thank you, sir.
Yeah, thank you. You watch my video lectures, and if you have any doubt, you can ask. So shall I then come out?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay.
Thank you,
Okay,
sir.
Thank you.
Thank you, sir.
Thank you.
Okay, I hope you have received the feedback link as well as the text link. It is also shared in the WhatsApp group. So I request all of you to give your valuable feedback as well as to appear the test before the midnight. So as a part of validatory function, I request all of you to give the verbal feedback, although you have given the written feedback. So any participants wants to give any verbal feedback, please unmute and introduce yourself and say something about this program. Please. Any participant? Yeah, Samim sir.
Yeah, good evening, sir. Sir, this is Savita Bansal. I'm working as assistant professor in Chandigarh University.
Yeah, madam.
Thank to all the coordinators who are organized this workshop. Thank you. It is means to say, according to me, just lack is key. You need to just make some group discussions between the participants. Otherwise, the FDP is really, really very helpful in my academics. Thank you, sir. Thank you, ma'am.
Thank you.
Thank you. Thank you, madam.
Any other participant?
Hello, sir.
Yeah,
Good
please.
evening. I am Mr. Nilesh Bhalerav, sir. I am a research scholar at NIT Trichy.
Okay.
My guide, Dr. Sai Krishna, sir, suggested me to attend this workshop.
Yeah.
And I am now beginning my research work, and I have to use optimization technique in my work. So this workshop is very useful and beneficial for me. It covered all the necessary and all aspect regarding optimizations. So thank you.
Yeah, thank you, Nilesh.
Thank you, Nilesh.
Any other participant? Okay, thank you everyone, and thank you to E&I City Academy for sponsoring this program. We'll process your certificate as soon as possible. And we hope that within 30 to 40 days you will get your hard copy of the certificate. You have already said your address in the registration form. So there is no need to send again your address. So whatever address you have written there, we'll post the certificate to that particular address. So we hope that you will also participate in other programs offered by E&I City and IT. Yeah, thank you everyone.
Sir, please
Thank you,
take one
everyone.
photograph of all
Thank
the
you very much.
Yeah. So if possible, please switch on the camera. We'll take a photo. Let me increase the number of this window. Yeah, thank you everyone. So I'm closing this meeting.